Hello and welcome. I'm so glad you're here. Tonight we're going to take a journey together, a quiet drift through space, through the cosmos that surrounds us, cradles us, and in a very real sense, created us. We'll explore the universe from its most familiar corners to its deepest mysteries, moving gently from one wonder to the next, letting each fact settle like snow on a winter evening. Maybe you've had a long day. Maybe your mind is still buzzing with the thousand small concerns that fill our waking hours. The emails, the conversations, the things left undone. That's all right. Let them be. For the next while, we're going to set all of that aside and think about something bigger, stranger, and ultimately more peaceful. The vast, patient universe that existed long before your worries and will continue long after they've dissolved into yesterday's forgotten dreams. Space is patient. It's been here for nearly 14 billion years, and it's not in any hurry. Neither are we. Before we begin, I'd love to hear from you. How was your day? What brought you here tonight? Take a moment, if you'd like, to write about it in the comments section below. And if you find yourself returning to this channel, if these cosmic bedtime stories help you find peace at the end of your day, consider subscribing. It helps us keep making these journeys for you. Now let's begin. When we think about space, we often imagine it as impossibly far away, something beyond our reach, belonging only to astronauts and spacecraft. But the truth is surprisingly intimate. Space officially begins at something called the Kármán line, just 62 miles above your head. 62 miles. That's closer than the distance between many neighboring cities. If you live in a place where you've driven an hour down the highway to visit family or see a concert, you've traveled farther across the surface of Earth than the distance straight up to where space begins. Think about that for a moment. The infinite cosmos, the realm of stars and galaxies and black holes, starts just an hour's drive away. If only you could drive upward. There's something both humbling and strangely comforting about this. Space isn't so remote after all. It's right there, just above the ceiling, beyond the clouds, past the thin blue shell of atmosphere that keeps us warm and breathing. We live at the bottom of an ocean of air, and just beyond its surface lies everything else. The Kármán line was named after Theodor von Kármán, a Hungarian-American physicist who calculated that at this altitude, the air becomes too thin for conventional aircraft to generate lift. Above this boundary, you're not flying anymore. You're orbiting, falling perpetually around the Earth, held up not by air but by the balance between gravity pulling you down and your sideways motion carrying you forward. It's a different kind of physics up there, a different set of rules. And it all begins just 62 miles up, close enough to almost touch. If you could somehow step outside your spacecraft and float freely among the stars, protected from the cold and the vacuum, just drifting there, you would notice something profound. Silence. Perfect, complete silence. Not the quiet of a library or the hush of snowfall, but true silence, the absence of sound itself. Sound, you see, is a wave that travels through matter. When you speak, your vocal cords vibrate, creating pressure waves that ripple through the air like waves across a pond. These compressions and rarefactions in the air molecules travel outward until they reach someone's ear, where tiny bones and delicate hairs translate those vibrations back into something the brain understands as voice, as music, as meaning. But sound needs something to travel through: air, water, metal, wood, anything made of molecules bumping into each other. Space has almost none of that. It's not completely empty. There are a few stray atoms scattered here and there. Perhaps one hydrogen atom per cubic centimeter in the better neighborhoods of the galaxy. But that's far, far too sparse to carry sound. There's nothing to bump into, nothing to vibrate. So when a star explodes in a supernova, releasing more energy than our sun will produce in its entire lifetime, it does so in absolute silence. All those dramatic explosions you've seen in space movies, the roaring engines and the thunderous blasts, they wouldn't make a whisper. The universe's most violent events happen without a sound, like watching a silent film, all light and fury signifying everything, but heard by no one. There's something almost meditative about this, isn't there? The cosmos is a place of profound quiet, despite all its violence and energy. Maybe that's part of what draws us to think about space as we fall asleep. It's the ultimate silent retreat, a place where the noise of the world simply cannot follow. Every year, the moon drifts a little farther from Earth. Not much, just about 1.5 inches, roughly the same rate your fingernails grow, but it's leaving nonetheless, pulling slowly away, receding into the darkness like a ship departing from shore, so gradually that you barely notice its movement until you compare where it is now to where it was years ago. This happens because of the tides. The moon's gravity pulls on Earth's oceans, creating the bulges of water we call high tide. But Earth is rotating faster than the moon orbits, so these tidal bulges are carried slightly ahead of the moon. The gravitational pull of these bulges tugs on the moon, gradually accelerating it in its orbit. And when something in orbit speeds up, it paradoxically moves to a higher, slower orbit, farther away. Meanwhile, this process gradually slows Earth's rotation, making our days longer, millisecond by millisecond, century by century. Billions of years ago, the moon was much closer. Days were shorter, perhaps just 5 or 6 hours long. The moon would have loomed enormous in the sky, creating tides hundreds of feet high. Imagine looking up and seeing the moon not as the gentle disk we know now, but as a massive, crater-marked face filling a substantial portion of the sky. It must have been spectacular and terrifying in equal measure. And billions of years from now, if Earth is still here, the moon will be much farther away, smaller in the sky, its pull weaker. Eventually, it might drift so far that total solar eclipses, those perfect alignments where the moon exactly covers the sun, will no longer be possible. We live in a cosmically fortunate moment when the moon is just the right distance to create those perfect, eerie daytime twilights. It's a temporary arrangement, a brief overlap in the long dance of celestial mechanics. Everything changes, even the distance to the moon, even the length of our days. Venus is strange in many ways, but perhaps the strangest is this: a single day on Venus, one complete rotation on its axis, takes longer than a year on Venus, one complete orbit around the sun. Let that settle in your mind for a moment. If you were standing on the surface of Venus, somehow protected from the crushing atmosphere and the searing heat, you would experience the sun slowly moving across the sky. Over the course of what we would call months, it would creep from horizon to horizon, and before it even completed one trip across the sky, before you'd seen one full day, the planet would have already gone all the way around the sun, Specifically, Venus takes 243 Earth days to rotate once on its axis, but only 225 Earth days to orbit the Sun. It's as if Venus is stubbornly turning in slow motion while everything else happens around it at normal speed. And there's more. Venus rotates backwards compared to most planets. If you could see the Sun through its thick, sulfurous clouds, it would rise in the west and set in the east, the opposite of Earth. Something in Venus's past, perhaps a massive collision, perhaps the complex gravitational interactions of its early history, left it spinning in retrograde, slowly, almost reluctantly. Time works differently there. The very definitions we use to organize our lives, day and night, the rhythm of sunrise and sunset, break down on Venus. It's a reminder that the patterns we take for granted, the cycles we build our calendars and our routines around, are local phenomena, accidents of where we happen to live. The universe has no obligation to make sense by our standards. Venus keeps its own time, slow and strange, indifferent to our expectations. When the Apollo astronauts stepped onto the surface of the moon, they left footprints. You've probably seen the photographs, clear, crisp impressions of boot treads in fine gray dust, evidence of humanity's brief visit to another world. What you might not know is that those footprints are still there, not fading, not eroding, but remaining almost exactly as they were when they were made more than 50 years ago. And they'll likely stay there for millions of years more. Here on Earth, footprints disappear. Wind scatters the dust, rain washes away the impression. Vegetation grows over the path. Time and weather erase our marks, smoothing everything back to unmarked ground. But the moon has no wind, no atmosphere to stir up breezes or storms. It has no rain, no rivers, no glaciers grinding slowly across its surface. Without these forces of erosion, things change very, very slowly. A footprint on the moon might eventually be erased by micrometeorites, tiny grains of dust traveling through space at thousands of miles per hour, slowly sandblasting the surface over millions of years. Or perhaps a larger meteorite might crash nearby, throwing up debris that buries the footprint. But barring such events, those impressions in the dust, marks of human feet, human presence, human wonder, will remain. There's something poetic about it. Long after the nations that sent those astronauts have changed or disappeared, long after the living memory of the Apollo program has faded, those footprints will persist, silent testimony to the time when beings from one world reached out to touch another. They're monuments now, not to individual astronauts, but to the audacity of exploration, to the strange fact that the universe allows its matter to organize itself into forms that can wonder about it, study it, and leave marks upon it. Somewhere up there, in airless silence, your species left footprints, and the moon, patient and unchanging, keeps them. Imagine holding something in your hand, a teaspoon, perhaps, the kind you'd use to stir sugar into your tea. Now imagine that instead of sugar or honey, that teaspoon held a piece of a neutron star. How much would it weigh? Not how much it would weigh on the neutron star, where gravity is inconceivably strong, but here, in your kitchen, subject to Earth's normal gravity, about 6 billion tons. 6 billion tons in a teaspoon. That's roughly the weight of 900 Great Pyramids of Giza, all compressed into something that could fit in the palm of your hand. The number is so large it becomes almost meaningless, the way very big numbers often do. but let's try to grasp it anyway. Neutron stars are what remain after certain massive stars explode in supernovae. The core of the star collapses inward under its own gravity, and the pressure becomes so intense that protons and electrons are forced together to form neutrons. The result is a sphere typically about 20 kilometers across, roughly the size of a city, but containing more mass than our entire sun. Its matter compressed to densities that would be impossible anywhere else, except perhaps in black holes. At those densities, the atoms as we know them cease to exist. There are no atoms, no molecules, no familiar structure, just neutrons packed together as tightly as the laws of physics will allow, touching each other in a sea of quantum degeneracy pressure. A single cubic centimeter of this material would weigh hundreds of millions of tons. It's hard to imagine, isn't it? Our brains didn't evolve to comprehend such extremes. We understand heavy things, a boulder, a car, a building. But 6 billion tons in a teaspoon breaks our intuition. And yet, scattered throughout the galaxy, there are thousands of these objects, each one a testament to what matter becomes when gravity compresses it beyond all familiar limits. The universe is stranger and more extreme than the everyday world suggests. Imagine waking up and seeing the sun rise, then just 92 minutes later, watching it set again, and then, an hour and a half after that, seeing it rise once more. This is the daily, or rather, not quite daily, rhythm of life aboard the International Space Station. The ISS orbits Earth once every 92 minutes, which means astronauts aboard experience 16 sunrises and 16 sunsets in what we would call a single day. The Earth turns beneath them, but they're moving so fast in their orbit that they outpace the planet's rotation, circling it more than 15 times while the surface completes just one turn. The sun appears and disappears with a regularity that has nothing to do with the 24-hour cycle our bodies evolved to expect. You might think they'd adjust, the way you adjust to a new time zone after a few days. But they don't, not really. The human circadian rhythm, the internal clock that tells us when to sleep and when to wake, runs on approximately a 24-hour cycle, synchronized over millions of years of evolution to Earth's rotation. 92 minutes is too fast, too divorced from our biological programming. So astronauts in space suffer from something called space insomnia. Their bodies never quite know when it's supposed to be night, never fully settle into the strange rhythm of 16 days and 16 nights compressed into one rotation of the clock. NASA has tried various solutions: sleep masks, scheduled light exposure, melatonin supplements, carefully timed work shifts. But sleep remains one of the most difficult challenges of long-duration spaceflight, perhaps more so than radiation or bone loss, or the psychological stress of confinement. There's something fundamental about our connection to the day-night cycle, something we don't fully appreciate until it's taken away. So the astronauts float in their sleeping bags, velcroed to the walls of the station, with masks over their eyes to block out the sunrise that comes too soon, again and again, 16 times a day. The sun insistently rising when their bodies cry out for darkness and rest. The light that's falling on your face right now, if you're near a window, or if you can see the stars, left the sun 8 minutes and 20 seconds ago. When you look at the sun, though, please don't look directly at it. You're not seeing it as it is now. You're seeing it as it was, a Little more than 8 minutes in the past. You're looking at history, at light that began its journey before you started reading this sentence. Light that has traveled 93 million miles through the vacuum of space to reach your eyes. This is because light, fast as it is not instantaneous. It travels at 186 sanas 282 miles per second, the fastest speed possible in our universe. Nothing can go faster, but even at that tremendous velocity, crossing the distance from the sun to Earth takes time. 8 minutes and 20 seconds to be precise. So in a very real sense, we never see the sun as it is. We see its past. If the sun were to suddenly vanish, just disappear, wink out of existence, we wouldn't know for 8 minutes and 20 seconds. We'd continue to see it, continue to feel its warmth, living in a bubble of outdated information, a temporary illusion sustained by the speed limit of the cosmos. Then all at once, the light would stop arriving, and we'd be plunged into darkness and cold. The sudden absence revealing what had already happened 8 minutes earlier. This isn't just true of the sun. Everything you see is the past. The light from the lamp across the room took a few nanoseconds to reach your eyes. The light from the moon is about 1.5 seconds old. Light from the nearest star system, Alpha Centauri, is 4 years old. You see those stars not as they are, but as they were 4 years ago, when that light began its journey. And when we look at distant galaxies, we're seeing them as they were millions or billions of years ago. Ancient light carrying images of a universe long changed. We live in the present, but we see the past. Every glimpse of the sky is a glimpse backward through time, a slow motion replay of the universe unfolding. Try to imagine all the beaches on Earth, every coastline, every sandy shore where waves lap against land. Picture the beaches you've visited, the feel of sand between your toes, the way it clings to wet skin, the countless tiny grains glittering in sunlight. Now expand that image to every beach everywhere, the long stretches of the Sahara that were once seabeds, the shores of every continent, every island, every lake with sandy banks. All of it, every single grain of sand. There are more stars in the observable universe than all of that sand combined. Astronomers estimate there are at least 100 billion trillion stars, a 1 followed by 23 zeros. It's a number so large it defeats comprehension. If you tried to count them, 1 per second, without sleeping or stopping, it would take you more than 3 billion years. You could count every heartbeat of your entire life and not reach even a tiny fraction of the total. And each of those stars is a sun. Each one is a massive sphere of nuclear fire, fusing hydrogen into helium, pouring energy into the darkness. Many of them are larger than our sun. Some are smaller, cooler, burning dimly for trillions of years. Others are blue giants, fierce and short-lived, burning through their fuel in just a few million years before exploding. Around many of these stars, planets orbit, worlds of rock and ice and gas, some perhaps with oceans, atmospheres, maybe even life. When you look up at the night sky, even from the darkest location on Earth, you can see perhaps a few thousand stars with your naked eye. That's all. Just a few thousand out of trillions upon trillions. It's like standing at the edge of an ocean and seeing only the nearest few drops of water. The rest extends beyond vision, beyond imagination, filling space with light and heat, and the possibility of worlds we'll never know. There are more stars than sand, The universe is, if nothing else, abundant. Here's a delightful thought. If you could find a bathtub large enough, and let's be honest, this is already stretching the imagination quite far, Saturn would float in it. This enormous planet, second largest in our solar system, 9 times the diameter of Earth, with those magnificent rings stretching hundreds of thousands of miles across, would bob on the surface like a cork. This is because Saturn is made mostly of hydrogen and helium, the 2 lightest elements, and lots of it is gas. Its average density is only about 0.687 grams per cubic centimeter, while water has a density of 1 gram per cubic centimeter. Anything less dense than water floats. Saturn is less dense than water. Therefore, Saturn floats. The logic is wonderfully, absurdly simple. Of course, the reality would be far more complicated and chaotic. Saturn is massive, 95 times the mass of Earth. Its gravity would pull the water toward it, disrupting any container. The heat from its interior would boil the water. The turbulence would be catastrophic. But if we're allowed to imagine a magical bathtub that could somehow contain Saturn and remain intact, then yes, it would float. A gas giant bobbing gently in an impossible ocean, its rings perhaps trailing in the cosmic bathwater. There's something charming about this fact, isn't there? Something that makes the vast and distant feel approachable, even playful. Saturn, that serene and beautiful giant, ruler of 62 moons, wrapped in golden clouds and crowned with icy rings. It's lighter than water. It reminds us that size and mass aren't the same thing, that the universe is full of surprising contrasts, and that even the most majestic objects follow the same simple rules of physics that govern whether a wooden boat or a rubber duck will float in your bath. You might think space would be odorless. After all, it's a vacuum, nearly empty, with nothing to carry scent molecules to your nose. And you'd be right, in a way. You can't smell space directly because you can't take off your helmet and breathe it in. But astronauts who've performed spacewalks report something curious. When they return to the airlock and remove their suits, there's a distinct smell clinging to the fabric, to their gloves, to any surface that was exposed to the void. They describe it as metallic, like hot metal or welding fumes. Some say it smells like seared steak, that particular charred meat aroma you get when fat hits a very hot grill. Others mention gunpowder or burning brake pads. It's not unpleasant exactly, but it's distinctive, sharp, industrial. The smell of something that's been through an intense process. What causes this? Scientists believe it's the result of polycyclic aromatic hydrocarbons, complex carbon molecules created in the dying gasps of stars billions of years ago, scattered throughout space and deposited on everything that ventures into the void. When these molecules encounter the oxygen-rich environment inside a spacecraft, they react, releasing their distinctive odor. So in a strange way, when astronauts smell space, they're smelling the remnants of ancient stars, the molecular debris of cosmic violence that happened long before Earth existed. It's a humbling thought. The smell of space is the smell of stellar death and creation, of fusion and explosion, of the cycle that turns hydrogen into all the heavier elements. Every atom of carbon that creates that metallic tang was forged in a star's core, or blown outward in a supernova. The astronauts are smelling history, chemistry, the very stuff that would eventually form planets and people. They're smelling where they came from. Imagine being born on Neptune. You would never live to see your first birthday, not because life there is short, but because a year on Neptune lasts 165 Earth years. One complete orbit around the Sun takes longer than the longest human lifespan ever recorded. You would be born, grow old, and die, all within a single Neptunian year, never seeing the seasons complete their cycle. Neptune is so far from the Sun, about 2.8 billion miles, that its orbit is vast, its journey slow. It moves through space at about 12,000 miles per hour, which sounds fast until you realize how much distance it has to cover. At that speed, going around the Sun takes nearly 2 centuries. When Neptune was discovered in 1846, the United States had just acquired Texas. The telegraph was cutting-edge technology. The concept of the telephone wouldn't emerge for another 30 years. And Neptune was just beginning its journey around the Sun. It wouldn't complete that first observed orbit until 2011. By then, we had computers, satellites, had walked on the Moon, sent probes to every planet. The world transformed entirely while Neptune made one slow, patient circle. It's still on that same orbit now, of course, the second one we've witnessed since discovering it. If you were to somehow stand on Neptune's surface, though it doesn't have a solid surface, just layers of gas growing denser until they become liquid and ice, you would see the Sun as merely a bright star, offering almost no warmth. The seasons, if you could call them that, would each last decades. Winter would be longer than a human lifetime. Spring would arrive to great-great-grandchildren. Time is relative, not just in Einstein's equations, but in the simple geometry of orbits. What we call a year is just one planet's particular dance with the Sun, and other planets waltz to very different rhythms. On the clearest, darkest nights, far from city lights, you can sometimes see a faint, fuzzy patch in the constellation Andromeda. It doesn't look like much with the naked eye, just a smudge of light, easily missed. But that smudge is the Andromeda Galaxy, a collection of 1 trillion stars, lying 2.5 million light-years away. It's the most distant thing you can see with your unaided eyes, and it's heading straight toward us. Andromeda is approaching the Milky Way at about 250,000 miles per hour. That's fast, unimaginably fast by human standards. But space is vast, and even at that tremendous speed, it will take about 4 billion years for the two galaxies to collide. 4 billion years. The Sun will have swelled into a red giant by then, possibly consuming Earth. Our planet's fate from solar expansion will likely be decided before the galactic collision ever matters to us. But when it happens, it will be spectacular. Not violent in the explosive sense. Galaxies are mostly empty space, and the odds of any individual star colliding with another are vanishingly small. But the gravitational interactions will reshape both galaxies. Stars will be flung into new orbits, some ejected into intergalactic space, others pulled inward toward the combined center. The spiral arms will distort, fragment, eventually merge into a new structure, probably a large elliptical galaxy, which future astronomers have playfully named Milkomeda. For anyone alive to witness it, though there will be no one, not as we know life now. The night sky will transform over millions of years. Andromeda will grow larger, its spiral structure becoming visible even without telescopes, until eventually the sky is full of stars from both galaxies, a richer, stranger tapestry than anything we see now. It will be chaos, but beautiful chaos. two great wheels of stars interpenetrating, dancing, becoming one. Everything moves toward everything else, pulled by gravity's patient hand. Even galaxies cannot stay apart forever. Here's something that sounds like science fiction, but is absolutely real. Time moves at different speeds, depending on how strong gravity is where you're standing. This is called gravitational time dilation, predicted by Einstein's general relativity and confirmed by countless experiments. Time is not the steady, universal metronome we imagine. It's flexible, malleable, dependent on where you are. If you stand at the top of a mountain and your friend stands at sea level, time passes slightly faster for you than for your friend. The difference is tiny. We're talking nanoseconds over a lifetime, but it's measurable with precise atomic clocks. GPS satellites have to account for this effect, or they'd accumulate errors of miles per day. The satellites orbit high above Earth, where gravity is slightly weaker, so their clocks run faster than clocks on the ground. Engineers have to program them to tick slightly slower to compensate. Near a black hole, where gravity becomes extreme, time dilation becomes dramatic. If you could somehow survive near the event horizon of a massive black hole and look back at the universe, you would see the stars aging rapidly, galaxies evolving, the cosmos rushing forward through time. Meanwhile, to someone watching you from a safe distance, you would appear to move in slow motion, your processes grinding nearly to a halt as you approach the point of no return. This isn't an illusion or a trick of perception. Time genuinely passes at different rates in different gravitational fields. There is no universal now that everyone agrees on. Your present moment and mine are slightly different if we're at different altitudes, different distances from massive objects. Time, that seemingly most absolute of measures, bends and stretches according to the curvature of space. It's enough to make you reconsider what time even is. Not a river flowing at constant speed, but something more like a landscape, with hills and valleys, places where it pools slowly, and places where it rushes by. The universe, on average, is cold. The cosmic microwave background, the faint afterglow of the Big Bang, has cooled over 13.8 billion years to about 2.7 degrees above absolute zero, which is roughly 270 degrees Celsius. That's the baseline temperature of empty space, the cold of the void itself. It's difficult to imagine cold that extreme. At those temperatures, most substances become brittle, frozen solid. Gases become liquids, become solids. Molecular motion slows to near stillness. But here's what's remarkable. The coldest known place in the universe isn't out there in the depths of space. It's here, on Earth, in a laboratory. Scientists have cooled atoms to less than 1/1000th of a degree above absolute zero, colder than anywhere naturally occurring in the cosmos. They've created a cold that the universe itself, even in its darkest, emptiest reaches, cannot match. They do this using lasers and magnetic fields, slowing down atoms until they barely move at all, until they enter strange quantum states where matter behaves in ways that defy common sense, becoming superfluids that flow without friction, or forming Bose-Einstein condensates, where thousands of atoms act as a single quantum entity. At these temperatures, the boundary between particle and wave becomes blurred, and matter reveals behaviors normally hidden by the thermal jitter of everyday temperatures. It's a curious inversion. We tend to think of space as the realm of extremes, of conditions we can never reproduce on Earth. And that's true for many things: the crushing gravity near black holes, the nuclear fires in stellar cores, the vast emptiness between galaxies. But in this one category, in the realm of perfect cold, we've surpassed the universe. Human ingenuity and curiosity have created conditions colder than anything nature provides. There's something quietly triumphant about that, isn't there? We may be small, confined to one tiny planet, but we can still reach beyond what the cosmos offers, probing the edges of physical law in the controlled environment of a laboratory, finding new extremes, new wonders. Mars is a dusty world. Its surface is covered in fine, rust-colored particles, iron oxide, the same stuff that makes old metal rust on Earth. The atmosphere is thin, just 1% the density of Earth's, but what little air exists can move very fast, driven by temperature differences between day and night, between equator and poles. And when the wind picks up, it lifts that dust, carries it for miles, for hundreds of miles, sometimes across the entire planet. The dust storms on Mars can be small and local, swirling dust devils that wander across the plains like terrestrial tornadoes. But they can also grow, merge, feed on each other's momentum until they engulf regions the size of continents. And occasionally, every few Martian years, the storms become global. The entire planet disappears beneath a haze of suspended dust, a shroud that can last for weeks or months. During these global dust storms, surface features vanish. If you were in orbit looking down, you wouldn't see the valleys or volcanoes or polar caps, just a uniform, featureless orange sphere, the whole world hidden beneath a veil of dust. Down on the surface, the sun becomes a dim glow. Daylight turns to perpetual twilight, and solar-powered rovers must hunker down and wait, surviving on battery reserves, hoping the storm passes before their power runs out. This is what happened to the Opportunity rover in 2018. A global dust storm blocked the sunlight. Its batteries depleted, and it fell silent. Engineers sent commands, hoping it would wake up when the storm cleared and sunlight returned. But it never responded. Somewhere on Mars, Opportunity sits quiet, covered in dust, its mission ended by the planet's fierce, patient winds. There's something melancholic about that image. A machine, built by humans 500 million miles away, designed to explore and discover, stopped not by mechanical failure but by weather, by the simple accumulation of dust blocking the light it needed. Mars is beautiful, but it's harsh. The thin air we imagine as gentle can become a world-covering tempest, reminding us that we've only just begun to understand the moods of other worlds. Our solar system feels like a collection of equals, 8 planets, or 9 if you have nostalgia for Pluto's planetary status, each with their own character, their own moons and features. We talk about them as if they're co-stars in the cosmic drama, sharing the stage. But the truth is more lopsided than that. The Sun accounts for 99.86% of all the mass in the solar system. Everything else, all the planets, all the moons, all the asteroids, all the comets, all the dust and ice and rock, makes up just 0.14%, barely more than a rounding error. Think about that. Jupiter, the giant among planets, more massive than all the other planets combined, is still just a fraction of a percent of the solar system's total mass. Earth is a speck, a mote, almost negligible in the accounting. We orbit within a system utterly dominated by one object, the massive sphere of nuclear fire at the center, and everything else is debris, remnants of the disk from which the sun formed, clinging to the edges, held in orbit by its overwhelming gravity. It's humbling, but also clarifying. The solar system isn't really a system of planets. It's the sun, and some stuff that happens to orbit it. The sun's gravity shapes everything, determines every orbit, every trajectory. Without it, the planets would simply fly off into space, no longer bound to anything, no longer a system at all. And yet, for all its dominance in mass, the sun is just one star among hundreds of billions in our galaxy, a middle-aged, medium-sized, unremarkable star burning steadily in an outer arm of the Milky Way. Dominant here, ordinary there. It's all a matter of perspective, of scale, of which context you choose to measure against. In our local neighborhood, the sun is everything. In the galaxy, it's one more point of light. When astronauts spend months aboard the International Space Station, they undergo many physical changes. Their bones lose density because there's no weight to bear. No stress to trigger the constant rebuilding that keeps bones strong. Their muscles atrophy for similar reasons. Without gravity, you don't need strong legs or a strong back just to stand and move. Their cardiovascular systems adapt to microgravity, and their immune systems weaken. But one change is more immediately noticeable and rather peculiar. They grow taller. Not permanently and not by much, typically about 2 inches, but it's measurable, visible, real. In the absence of gravity, the spine decompresses. On Earth, the weight of your head and upper body constantly presses down on the discs between your vertebrae, squishing them slightly, keeping you compressed. In space, that weight disappears. The discs expand, the spine lengthens, and astronauts find themselves floating around the station a little taller than they were at launch. It's not necessarily comfortable. Many astronauts report back pain, especially in the first few days, as their spines adjust to the new configuration. The muscles and ligaments that normally support the compressed spine suddenly have to adapt to a different structure. And when they return to Earth, gravity reasserts itself, compressing them back to their original height over the course of a few days or weeks. That readjustment can be uncomfortable too, aches and pains as everything settles back into place. There's something almost comical about it, this temporary height gain, as if space grants you a brief boost before taking it away when you come home. But it also serves as a reminder that our bodies are deeply adapted to life under one gravity, on one planet. We evolved here, shaped by the constant pull downward, and even something as fundamental as our height is maintained by that pull. Remove it, and we change, our bodies responding to new conditions, becoming versions of ourselves that are just slightly different, stretched and altered by the environment we find ourselves in. The sun appears to us as a smooth, bright disk in the sky, sometimes yellow, sometimes white, sometimes red at sunset, depending on how much atmosphere its light passes through. It seems constant, steady, unchanging from day to day. But inside, at its core, something extraordinary is happening. The temperature there reaches about 27 million degrees Fahrenheit. And under that intense heat and crushing pressure, hydrogen atoms slam into each other with enough force to overcome their electromagnetic repulsion and fuse together, forming helium. This is nuclear fusion, the process that powers the sun, that powers all stars. Every second, the sun converts about 600 million tons of hydrogen into helium, and in that process, About 4 million tons of matter is transformed into pure energy according to Einstein's famous equation E or mc2. That energy radiates outward as light and heat, the same sunlight that warms your skin, that drives Earth's weather, that powers photosynthesis, and ultimately supports all life on this planet. But here's the strange part. The energy created in the core doesn't reach the surface instantly. It's produced in the form of high-energy gamma rays, and those photons begin a long, chaotic journey outward. They travel a short distance, then collide with an atom, and get absorbed and re-emitted in a random direction. They bounce around inside the sun like a ball in an enormous, dense pinball machine, slowly making their way toward the surface through countless collisions, absorptions, and re-emissions. This journey takes about 100,000 years. The light that reaches your eyes today, that left the sun's surface 8 minutes ago, was actually created in the core roughly 100,000 years ago. It's ancient light, older than human civilization, born when our ancestors were still living in small hunter-gatherer bands, slowly working its way through the sun's interior until finally breaking free and racing across space to arrive here. Now, at this moment, to be absorbed by your retina and converted into the image of the sun. Every sunrise is a glimpse of the deep past, energy that has been traveling toward this moment for longer than recorded history. Let's try to grasp this number. There are at least 100 billion galaxies in the observable universe. 100 billion. Each one a vast collection of stars, some containing a few billion, others containing trillions. Each galaxy an island universe unto itself, separated from the others by millions of light years of mostly empty space. And remember, each of those galaxies contains billions to trillions of stars. So when we calculated earlier that there are more stars than grains of sand on all Earth's beaches, that wasn't an exaggeration or poetic license. It was a conservative estimate. The universe is absurdly, almost offensively abundant with stars, with light, with matter organized into burning spheres of nuclear fusion. But even more remarkable than the number of galaxies is this. The observable universe represents only what light has had time to reach us since the Big Bang. It's a sphere centered on Earth, extending about 46.5 billion light years in every direction. It's larger than 13.8 billion light years, because space itself has been expanding while the light traveled. But the universe doesn't end at the edge of what we can observe. It extends beyond, possibly infinitely, filled with galaxies we will never see because their light hasn't had time to reach us yet, or because they're moving away so fast due to cosmic expansion that their light will never reach us. So those 100 billion galaxies might be just a tiny fraction of what exists. The full universe could be incomprehensibly larger, containing numbers of galaxies that have no meaningful names, extending perhaps forever in all directions. An infinity of islands of stars in an infinite sea of space. It makes our concerns feel very small, doesn't it? But also, somehow, connected to something vast. We are made of matter that came from stars in one of those galaxies, organized into a form that can look outward and count the other galaxies, measure their distances, understand their nature. The universe contemplating itself, one small piece of it becoming aware and curious. That's worth something, even in a cosmos of 100 billion galaxies. Jupiter's great red spot is a storm, not a weather system that lasts a few days or weeks, like hurricanes on Earth, but a storm that has been raging for at least 350 years, possibly much longer. We've been observing it since the 1600s, when early telescopes first revealed the banded clouds and the massive oval of churning atmosphere. And it's still there, still spinning, still dominating the planet's southern hemisphere. The storm is enormous. At its largest, it was wide enough to fit 2 or 3 Earths inside. Imagine that. A hurricane the size of multiple planets, winds howling at hundreds of miles per hour. A vortex that has outlasted empires, outlasted entire civilizations. When Galileo first turned his telescope toward Jupiter, this storm may have already been ancient, but it's shrinking. Observations over the past century show the Great Red Spot getting smaller, its boundaries contracting. No one knows exactly why or whether it will eventually disappear entirely or stabilize at a smaller size. Some astronomers think it might fade away within our lifetimes, ending a storm that has raged since before the Industrial Revolution. There's something melancholic about watching it shrink, this ancient feature slowly dying. But storms, even storms that last centuries, aren't eternal. They're patterns of flow, temporary organizations of energy and matter that persist until conditions change. The Great Red Spot has had a remarkable run, but nothing lasts forever. Not storms, not stars, not galaxies. Everything in the universe is temporary, just operating on different timescales. In 1977, NASA launched 2 spacecraft, Voyager 1 and Voyager 2. Their primary mission was to explore the outer planets, Jupiter, Saturn, and in Voyager 2's case, Uranus and Neptune. They succeeded beautifully, sending back stunning images and data that transformed our understanding of these distant worlds. But their journey didn't end there. The Voyagers kept going, kept flying outward, beyond the planets, beyond Pluto's orbit, into the vast emptiness between stars. And they're still going. Voyager 1 is now more than 15 billion miles from Earth, so far away that radio signals, traveling at the speed of light, take over 22 hours to make the one-way trip. If you send a command to Voyager, you have to wait almost 2 days to hear back that it received the message. Attached to each Voyager is a golden record, a literal phonograph record made of gold-plated copper, containing sounds and images from Earth. There are greetings in 55 languages, music from different cultures and eras, sounds of wind and rain and laughter, images of people and places and mathematical diagrams. It's a message to any intelligence that might one day find these spacecraft drifting through the galaxy. A note saying, "We were here. This is what we were like. This is the world we came from." The odds of anyone finding them are vanishingly small. Space is vast, and the Voyagers are tiny, silent now except for their faint transmitters, coasting on momentum through the dark. But they carry that record anyway, that hopeful gesture toward an unknown future. A message in a bottle thrown into an ocean larger than imagination. In 40,000 years, Voyager 1 will pass within about 1.5 light years of a star. Maybe, impossibly, someone will be there to see it drift by. Mercury, the closest planet to the Sun, experiences the most extreme temperature variations in the solar system. During its long day, which lasts 59 Earth days, the sun-facing side bakes under intense radiation, reaching temperatures around 800 degrees Fahrenheit, hot enough to melt lead. But at night, which also lasts 59 Earth days, that same surface plunges to 290 degrees Fahrenheit, colder than the coldest places on Earth. The swing is over 1,000 degrees, from scorching to frigid, all on the same spot of ground as Mercury rotates. Why such extremes? Mercury has almost no atmosphere, just a thin exosphere of atoms blasted off its surface by solar wind. Without an atmosphere to trap and redistribute heat, the side facing the sun roasts, while the night side radiates its heat directly into space, cooling to temperatures limited only by the background cold of the universe itself. On Earth, our atmosphere acts like a blanket, holding warmth, moderating temperatures between day and night, between equator and poles. Even in deserts, where day-night temperature swings can be dramatic, they're nothing compared to Mercury. Our atmosphere protects us, keeps us in a narrow, comfortable range where water stays liquid and life can thrive. Mercury has no such buffer. It's naked to space, vulnerable to the sun's fury and the void's cold in equal measure. Standing on Mercury's surface, you could watch the sun slowly crawl across the sky over weeks. Feel the temperature gradually rising to unbearable heat, then weeks later plummeting to bone-cracking cold. It's a world of extremes, of harsh contrasts, beautiful in its desolation, but utterly inhospitable. The Hubble Space Telescope was launched in 1990, carried into orbit by the Space Shuttle Discovery, and released to begin its mission of observing the universe from above Earth's atmosphere. That atmosphere, while essential for life, is terrible for astronomy. Air turbulence makes stars twinkle, which is poetic, but frustrating for scientists trying to measure their properties. Water vapor and other molecules absorb certain wavelengths of light. The glow of city lights, scattered by the atmosphere, washes out faint objects. But above the atmosphere, in the clarity of space, Hubble could see with unprecedented sharpness. Over the past 3 decades, it has taken more than 1.5 million observations, peering at planets in our solar system, stars being born in nearby nebulae, galaxies billions of light years away, and the dark reaches between galaxies where gravity lenses light around invisible mass. Those images, the pillars of creation, the Hubble Deep Field, the countless colorful nebulae and spiral galaxies, have become iconic, part of our visual vocabulary for what the universe looks like. They've appeared on posters, in documentaries, in classrooms, inspiring generations to look up and wonder. But beyond their beauty, Hubble's observations have revolutionized astronomy, helping to determine the age of the universe, discovering dark energy, revealing the prevalence of black holes, observing distant supernovae, studying exoplanet atmospheres. Hubble is aging now. Its instruments occasionally fail, requiring creative workarounds by engineers on the ground. Its eventual successor, the James Webb Space Telescope, has already launched and begun its own observations. But Hubble continues, still working, still peering into the cosmos, still sending back images of wonder from its perch above the world. Mars is home to Olympus Mons, the largest volcano in the solar system. It rises about 13.6 miles above the surrounding plains, nearly 3 times the height of Mount Everest. But its base is even more impressive, stretching about 370 miles across, roughly the size of the state of Arizona. If you stood at the center and looked toward the edge, the rim would be beyond the horizon, hidden by the curvature of Mars itself. Olympus Mons is a shield volcano, built up over millions of years by countless eruptions of fluid lava that spread outward in thin layers, gradually building the mountain higher and wider. It's similar in structure to Hawaiian volcanoes, but vastly larger, in part because Mars has lower gravity, allowing lava to pile higher before collapsing, and in part because Mars lacks plate tectonics. On Earth, the volcanic hotspot that created Hawaii stays in one place while the tectonic plate moves over it, creating a chain of islands. On Mars, the crust stays put, so eruptions keep adding to the same spot, building one enormous mountain instead of a chain. The volcano is likely extinct now. No one has observed any recent activity, and the surface appears ancient and cratered. But geologically, extinct is provisional. Mars might still have internal heat, and Olympus Mons might erupt again someday, adding new layers to its already staggering height. Or it might be truly dead, a monument to a time when Mars was geologically active, when lava flowed and the planet's interior churned with heat. Either way, it stands there, the tallest mountain in the solar system, a reminder that other worlds have their own wonders, their own extremes that dwarf anything Earth can offer. Every other planet in our solar system is named after a god or goddess from Roman mythology. Mercury, the swift messenger; Venus, the goddess of love and beauty; Mars, the god of war; Jupiter, king of the gods; Saturn, god of agriculture and time; Uranus and Neptune, gods of the sky and sea. Even dwarf planets follow this tradition: Pluto, god of the underworld, and others named for various deities and mythological figures. But Earth comes from Old English and Germanic words, Jorte in Old English, Erde in German, meaning simply the ground or soil. It's a humble, practical name, referring to the dirt beneath our feet, the land we walk on. No grand mythology, no divine association, just a word for the substance we stand on. There's something endearing about this. All the other planets get dramatic, mythological names suggesting power and mystery, while we call our own planet dirt. It reflects perhaps how long humans thought of Earth not as a planet, a wandering star, a world among worlds, but as the ground, the foundation, the entirety of existence. The other planets were lights in the sky, mysterious and distant, worthy of God's names. Earth was just here, the place where things happened. Of course, now we know Earth is a planet too, orbiting the sun just like the others, subject to the same physical laws. It's a world, not the world, but the name remains, a linguistic artifact from a time when we saw ourselves as separate from the cosmos, not part of it. Earth, the ground, home. Despite being the largest planet in our solar system, more massive than all the other planets combined, Jupiter spins faster than any of them. A day on Jupiter lasts only about 10 hours. 10 hours for a planet 11 times the diameter of Earth to complete one full rotation. That's extraordinarily fast. This rapid rotation has consequences. Jupiter bulges noticeably at its equator, flattened by centrifugal force. The equatorial diameter is about 88,000 miles, while the polar diameter is about 83,000 miles. It's visibly not spherical, but ellipsoidal, squeezed at the poles and bulging at the middle like a ball of clay spinning on a potter's wheel. The rapid rotation also creates powerful atmospheric currents. Jupiter's clouds are organized into bands that circle the planet, driven by the Coriolis effect and the planet's internal heat. These bands move at different speeds, creating shear zones where they meet, and in those zones, turbulence and storms arise. The Great Red Spot exists at one such boundary, fed by the energy of different wind speeds colliding. From Earth, even through a modest telescope, you can see these cloud bands, the alternating light and dark stripes wrapping around Jupiter. And if you watch over the course of a single night, you can see the planet rotate, features appearing and disappearing over the limb as Jupiter spins. It's hypnotic, this giant world turning so quickly, so visibly, a reminder that planets aren't static objects, but dynamic, rotating, evolving systems. When you hear asteroid belt, you might imagine a dense field of tumbling rocks, so thick that spacecraft have to carefully navigate through them, dodging boulders like in a science fiction movie. But the reality is far emptier. The asteroid belt, which lies between Mars and Jupiter, does contain millions of asteroids, chunks of rock and metal ranging from dust grains to Ceres, which is about 590 miles across. But they're spread over such a vast volume of space that they're incredibly sparse. If you were flying through the asteroid belt in a spacecraft, the odds are overwhelming that you wouldn't see a single asteroid out your window. Not one. You'd have to deliberately aim for one if you wanted a close encounter. The average distance between asteroids is hundreds of thousands of miles. Space is vast, and even millions of objects become vanishingly rare when distributed across the enormous volume between Mars and Jupiter. Every spacecraft we've sent to the outer solar system has passed through the asteroid belt without incident, without even having to maneuver to avoid anything. The Voyagers, Cassini, New Horizons, they all sailed through as if through empty space, because functionally, it is empty space with occasional rocks scattered so far apart they might as well not be there. This is another reminder that space is mostly space, emptiness, vacuum, absence. The universe is defined more by what's not there than what is. Even in a region named for the objects it contains, the dominant feature is the nothingness between them. When the New Horizons spacecraft flew past Pluto in 2015, after a 9-year journey across the solar system, it revealed a world far more complex and beautiful than anyone expected. Pluto had been demoted to dwarf planet status in 2006, reclassified as just one of many objects in the Kuiper Belt. But the images from New Horizons showed a planet, dwarf or not, with mountains of water ice, nitrogen glaciers flowing in slow motion, and a bright, heart-shaped region on its surface. That heart-shaped feature, named Tombaugh Regio after Pluto's discoverer, Clyde Tombaugh, is a plain of frozen nitrogen larger than Texas. It's bright white, reflecting sunlight, standing out against the darker, reddish terrain around it. The nitrogen ice flows like a glacier, albeit slowly given Pluto's frigid temperatures of around 375 degrees Fahrenheit. Scientists think this ice is constantly, though slowly, sublimating, turning from solid directly into gas on the sunlit side and condensing back into ice on the colder side, creating a cycle of evaporation and refreezing that continually renews the surface, keeping it smooth and crater-free. It's a dynamic process on a world so far from the sun that sunlight is 1,000 times dimmer than on Earth, where you'd barely feel its warmth. Pluto surprised us. It wasn't the dead, boring rock many expected, but a geologically active world with weather, seasons, and surface processes. The heart seemed almost like a message, a reminder that even at the edge of the solar system, in the cold and dark, there's beauty and complexity waiting to be discovered. The sun is losing mass constantly, every single second of every single day. It's not breaking apart or decaying. This is a natural consequence of nuclear fusion. In the core, hydrogen fuses into helium, and in that process, a tiny amount of mass is converted into energy, according to Einstein's equation, E or mc2. That energy radiates outward as light and heat, and once it's left the sun, it's gone. The mass that became that energy is lost. The rate of loss is about 4 million tons per second. 4 million tons. That's an incomprehensibly large number, the equivalent of thousands of aircraft carriers worth of mass vanishing every second. And yet, the sun is so massive, about 2 x 10 or 30 kilograms, a 2 followed by 30 zeros, that even losing 4 million tons per second, it can sustain this process for billions of years. In fact, despite losing 4 million tons every second for the past 4.6 billion years, the sun has lost only a tiny fraction of its total mass. It's been burning steadily, pouring energy into the solar system, warming planets, enabling life on Earth, and it still has enough hydrogen fuel to continue for another 5 billion years before it exhausts its core supply and begins to die. It's a reminder of the scales involved in stellar processes, numbers that would be catastrophic on human or even planetary scales. Losing millions of tons per second are trivial to a star. The sun burns with such profligacy, such abundance, that it can afford to lose mass forever, from our perspective, and barely notice. Most planets spin roughly upright, their rotation axes tilted only slightly from perpendicular to their orbital plane. Earth tilts about 23.5 degrees, giving us seasons as different hemispheres lean toward or away from the sun. Mars tilts similarly. Even Jupiter and Saturn have modest tilts, but Uranus is different. Uranus rotates on its side, tilted 98 degrees, essentially rolling around the sun like a ball rather than spinning like a top. This means Uranus experiences the most extreme seasons in the solar system. Each pole gets 42 years of continuous sunlight, followed by 42 years of complete darkness. Imagine 4 decades of day, then 4 decades of night. During summer at the North Pole, the sun would circle the sky, never setting, slowly spiraling higher and lower over the decades, but never dipping below the horizon. Then, as Uranus moves in its orbit, the sun would finally set and not rise again for another 42 years. What caused this bizarre tilt? Most scientists believe Uranus suffered a massive collision early in its history, perhaps with an Earth-sized object or multiple smaller impacts that knocked it over onto its side. The violence of the early solar system, when planets were still forming and collisions were common, left permanent scars. Uranus's sideways spin is one such scar, a reminder that planetary formation wasn't gentle, but chaotic and violent. The planet's magnetic field is tilted too, offset from both the rotation axis and the planet's center, creating a lopsided magnetosphere that wobbles as Uranus spins. Everything about Uranus feels slightly wrong, slightly off-kilter, as if the universe took a perfectly normal ice giant and gave it a hard shove, leaving it forever altered. The speed of light, 186,282 miles per second, or about 300,000 kilometers per second, is the universe's ultimate speed limit. According to Einstein's theory of special relativity, nothing with mass can reach this speed, let alone exceed it. Light itself, photons which have no mass, travels at this speed through vacuum, and it's the fastest anything can go. Why this limit? The mathematics of relativity show that as an object approaches light speed, its mass effectively increases, requiring more and more energy to accelerate further. To actually reach light speed would require infinite energy, which is impossible. So matter is forever confined to speeds below this threshold, always approaching but never reaching the speed of light. This has profound consequences. It makes interstellar travel extraordinarily difficult. Even traveling at 90% of light speed, which would require technology far beyond anything we possess. A trip to the nearest star system, Alpha Centauri, would take nearly 5 years. More distant stars would take decades, centuries, millennia. The galaxy is vast, and light speed, fast as it is, isn't fast enough to make it feel small. Some physicists speculate about theoretical ways around this. Warp drives that bend space itself, wormholes connecting distant points. But these remain entirely speculative, requiring exotic matter or energy conditions we're not sure exist. For now, the speed of light remains an absolute barrier, written into the fundamental laws of physics. It's a strange constraint when you think about it. The universe is vast beyond comprehension, filled with wonders, separated by distances light takes years or millennia to cross, and the fastest possible speed still leaves almost everything forever out of reach. Saturn's rings are magnificent, stretching about 175,000 miles from edge to edge, wide enough to fit more than 2 Earths side by side between the inner and outer edges. They're visible from Earth through even a modest telescope, tilted at various angles as Saturn orbits the Sun, sometimes edge-on, when they nearly disappear from view, sometimes face-on, when they appear at their most spectacular. But despite their vast extent, the rings are astonishingly thin, mostly less than 30 feet thick. 30 feet. If you scaled the rings down to the size of a football field, they'd be thinner than a sheet of paper, thinner than a razor blade. They're composed of billions, perhaps trillions, of individual chunks of ice and rock, ranging from dust grain-sized particles to boulders as large as houses, each one orbiting Saturn independently. Why so thin? The particles naturally settle into a flat plane due to collisions and gravitational interactions. If a particle orbits slightly above or below the main plane, it will eventually collide with others, and those collisions damp out vertical motion, flattening the distribution. Over time, the rings become thinner and thinner, approaching, though never quite reaching, a perfectly flat disk. The rings aren't permanent. They're slowly spiraling inward, raining down onto Saturn as particles lose energy and fall toward the planet. Scientists estimate the rings might be relatively young, perhaps only a few 100 million years old, and might disappear entirely in another 100 million years. Saturn hasn't always had rings, and won't always have them. We're lucky to live in an era when they exist, and we can observe them in their frozen, temporary glory. The sun doesn't just emit light and heat. It also constantly streams charged particles outward in all directions. This flow, called the solar wind, consists mainly of electrons and protons, racing away from the sun at about 1 million miles per hour. It's thin, far more tenuous than even the best vacuum we can create on Earth, but it fills the solar system, flowing past all the planets, extending billions of miles until it finally encounters the interstellar medium and slows down. Earth sits immersed in the solar wind, but we're protected by our magnetic field. The planet's molten iron core generates a magnetic field that extends thousands of miles into space, creating a protective bubble called the magnetosphere. When solar wind particles hit this magnetic field, most are deflected around the planet, channeled away from the surface. We're safe, shielded from this constant bombardment of radiation. But some particles get funneled along magnetic field lines toward the poles, where they collide with atoms in the upper atmosphere. These collisions excite the atoms, causing them to emit light, creating the aurora borealis in the north and aurora australis in the south. Those shimmering curtains of green, red, and purple light are visible evidence of invisible particles from the sun interacting with our atmosphere, painting the sky with energy. The solar wind isn't constant, it varies with solar activity. During solar storms, the sun can eject massive bursts of particles in events called coronal mass ejections. When these reach Earth, they can cause spectacular auroras visible at lower latitudes than usual. But they can also disrupt satellites, radio communications, and power grids. The sun, for all its life-giving warmth, is also a source of radiation that would be lethal without Earth's protective magnetic shield. Europa, one of Jupiter's largest moons, appears at first glance to be a dead, frozen world. Its surface is covered in ice, crisscrossed with long, dark streaks and relatively few craters, suggesting the surface is young, constantly renewed by geological processes. But beneath that icy shell lies something extraordinary, a global ocean of liquid water, possibly containing twice as much water as all of Earth's oceans combined. The evidence comes from multiple sources. Europa's surface features suggest the ice floats on liquid water beneath, cracking and refreezing in patterns consistent with an ocean below. Measurements of Europa's magnetic field show it's induced by Jupiter's powerful magnetosphere, which would happen if there's a conducting layer beneath the surface, like salty water. And observations of water geysers erupting from Europa's surface suggest the ocean occasionally breaks through cracks in the ice. What keeps the ocean liquid? Europa orbits Jupiter in an elliptical path, and Jupiter's gravity squeezes and stretches the moon as it orbits, generating tidal heating, friction that warms Europa's interior. This heat, combined with possible radioactive decay in the rocky core, keeps water liquid beneath the ice, despite surface temperatures around 260 degrees Fahrenheit. This makes Europa one of the most promising places to search for life beyond Earth. On Earth, wherever we find liquid water, we find life. In the deepest oceans, in Antarctic lakes buried beneath ice, in hydrothermal vents where no sunlight reaches. If Europa's ocean exists, and if it has similar conditions, warmth from hydrothermal vents, dissolved minerals, energy sources, it might harbor life, organisms adapted to eternal darkness beneath miles of ice, swimming in an alien ocean we've never seen. Out beyond Neptune, in the region called the Kuiper Belt, where countless icy bodies orbit the sun, there's a dwarf planet named Haumea. It's about the size of Pluto, composed mostly of rock and ice, orbiting the sun once every 285 years. But Haumea has a peculiar feature. It spins extraordinarily fast, completing one rotation in less than 4 hours, faster than any other known object in the solar system larger than 60 miles across. This rapid spin has deformed Haumea into an elongated ellipsoid shape, like a stretched-out football or rugby ball. Instead of being spherical like most planets and large moons, Haumea is about 100 miles long, but only 600 miles wide, roughly twice as long as it is wide. Centrifugal force from the rapid rotation pulls material outward at the equator, stretching the dwarf planet into this odd shape. What caused this rapid spin? Likely a massive collision early in Haumea's history. Such an impact would have imparted angular momentum, setting Haumea spinning and possibly ejecting material that became its two known moons and a family of smaller objects sharing similar orbits. The violence of that ancient collision is still visible today in Haumea's shape, billions of years later. Imagine standing on Haumea's surface. Day and night would cycle in less than 4 hours. The sun rising, crossing the sky, and setting again before you'd finished a typical work shift. The horizon would curve strangely, more steeply in one direction than another, due to the ellipsoidal shape. And overhead, the stars would wheel past rapidly, completing their circuit 16 times in what we'd call a single day. Ceres is the largest object in the asteroid belt, about 590 miles in diameter, large enough that gravity has pulled it into a roughly spherical shape, qualifying it as a dwarf planet. For a long time, Ceres was thought to be just a large asteroid, a rocky body perhaps with some ice mixed in. But observations from NASA's Dawn spacecraft, which orbited Ceres from 2015 to 2018, revealed something surprising. Ceres contains more fresh water than Earth does, not liquid water on the surface. Ceres is too cold and has no atmosphere to keep water stable, but water ice mixed into the interior, and possibly a subsurface ocean or pockets of briny liquid beneath the crust. The evidence includes bright spots on Ceres's surface, particularly in a crater called Okator, where salt deposits and ice have been exposed. These deposits suggest that salty water from below occasionally reaches the surface, evaporates, and leaves behind mineral residues. Why does this matter? Ceres formed in the outer solar system where water ice was abundant, and over billions of years, collisions and gravitational interactions scattered such objects throughout the solar system. Understanding Ceres helps us understand how water, essential for life as we know it, got distributed to Earth and other planets. Perhaps impacts by Ceres-like objects delivered much of Earth's water early in our planet's history. Ceres is a time capsule, preserving conditions from the early solar system, holding secrets about how planets formed and how the ingredients for life spread through our cosmic neighborhood. And it's right there, relatively close, in the asteroid belt between Mars and Jupiter, patiently orbiting, waiting to tell us more. Jupiter, the giant of our solar system, plays an important role in protecting Earth from impacts. Its massive gravity, more than twice the gravity of all other planets combined, acts like a cosmic vacuum cleaner, deflecting or capturing comets and asteroids that might otherwise wander into the inner solar system and potentially collide with Earth. When a comet falls into the inner solar system from the distant Oort cloud, its path can be altered by Jupiter's gravity. Sometimes Jupiter flings the comet back outward or into the Sun. Sometimes it captures the comet into orbit around itself. In 1994, astronomers watched as comet Shoemaker-Levy 9 broke apart and slammed into Jupiter in a spectacular series of impacts, leaving dark scars visible even through amateur telescopes. Without Jupiter, Earth might have been hit by far more large impacts over its history. More frequent bombardment could have disrupted the development of complex life, perhaps preventing multicellular organisms from gaining a foothold, or causing mass extinctions more often than has actually occurred. We owe some debt to Jupiter, the protective giant standing guard in the outer solar system. Of course, Jupiter's influence isn't always protective. Its gravity can also deflect objects toward the inner solar system occasionally. But on balance, simulations suggest Jupiter's presence has reduced the impact rate on Earth significantly. We're fortunate to have this massive neighbor, and fortunate it formed where it did, large enough and positioned well enough to shield us from many dangers. Titan, Saturn's largest moon, is the only moon in the solar system with a thick atmosphere. In fact, its atmosphere is denser than Earth's. At Titan's surface, atmospheric pressure is about 50% higher than Earth's at sea level. This thick, hazy atmosphere is mostly nitrogen, with some methane, and it's so opaque that you can't see the surface from space with visible light. Titan appears as a featureless orange sphere, its surface hidden beneath layers of organic smog. But beneath that haze lies a remarkable landscape. Titan has weather, seasons, and a hydrological cycle similar to Earth's, except instead of water, it's methane. On Titan, where surface temperatures hover around 290 degrees Fahrenheit, methane can exist as a solid, liquid, or gas just like water on Earth. Methane rain falls from clouds, forming rivers that flow into lakes and seas. The largest sea, Kraken Mare, is bigger than the Caspian Sea on Earth. Imagine standing on Titan's surface. The sky would be orange, the haze scattering light into a perpetual twilight, even during the day. In the distance, you might see clouds gathering, and later, methane rain falling in large, slow-motion drops due to the thick atmosphere and low gravity. Liquid methane pools on the ground, forming puddles and streams that eventually drain into the seas. Titan is perhaps the most Earth-like world in the solar system in terms of having a complex, active surface with weather and erosion, just at temperatures so cold that methane replaces water and the ground is made of water ice as hard as rock. All the planets in our solar system orbit the Sun in roughly the same plane, as if they're all rolling along an invisible flat disk. This isn't a coincidence. It's a direct consequence of how the solar system formed. About 4.6 billion years ago, a cloud of gas and dust began to collapse under its own gravity. As it collapsed, it started spinning, and that spin caused the cloud to flatten into a disk, much like pizza dough flattens when you spin it. Within this rotating disk, particles collided and stuck together, gradually building up larger and larger objects. Dust grains became pebbles, pebbles became boulders, boulders became planetesimals, and planetesimals became planets. Because everything formed from the same rotating disk, everything inherited the disk's rotation, orbiting in the same direction and in roughly the same plane. You can see this alignment if you look at a diagram of the solar system from the side. All the planets' orbits lie within a relatively thin sheet of space. There are small deviations. Pluto's orbit is tilted about 17 degrees, Mercury's about 7 degrees. But overall, the alignment is striking. Even the Sun's equator aligns roughly with the planetary plane, because the Sun formed from the same rotating cloud. This pattern isn't unique to our solar system. Around other stars, we've observed similar disk structures where planets are forming, and the planets we've detected around other stars also tend to orbit in aligned planes. It's a universal pattern, a signature of how gravity and rotation shape collapsing clouds into orderly, disk-shaped systems from which planets emerge. When a massive star, one at least 8 times the mass of the Sun, reaches the end of its life, It dies in one of the universe's most violent events, a supernova. The star's core, having fused lighter elements into iron, can no longer generate energy through fusion. Without the outward pressure of fusion to counteract gravity, the core collapses catastrophically in less than a second, then rebounds in a shockwave that tears the star apart. For a brief time, days to weeks, that single dying star outshines an entire galaxy of hundreds, billions of stars. Think about that. One star, in its death throes, releases more light than billions of other stars combined. From across the universe, a supernova can be visible as a new point of light where none existed before, sometimes bright enough to see during the day. The energy released is staggering. In those few seconds of core collapse and explosion, the supernova releases more energy than our sun will produce over its entire 10 billion year lifetime. Most of that energy comes out as neutrinos, ghostly particles that barely interact with matter. But even the tiny fraction that becomes light is enough to briefly dominate the sky. Supernovae are also creation events. The explosion forges heavy elements, gold, silver, uranium, all the elements heavier than iron, in the intense heat and pressure of the blast, then scatters them into space. These elements eventually become part of new star systems, new planets. Every atom of gold in your jewelry, every atom of calcium in your bones was created in a supernova explosion billions of years ago. We are, quite literally, made of stardust, the ashes of ancient stellar explosions. Our galaxy, the Milky Way, is a barred spiral galaxy about 100,000 light-years across. To cross from one edge to the other, traveling at the speed of light, would take 100,000 years. Even light, the fastest thing in the universe, would need 100 millennia to make the journey. And we, traveling at speeds achievable with current technology, would need millions or even billions of years. The Milky Way contains between 100 and 400 billion stars. The exact number is uncertain because much of the galaxy is obscured by dust, and counting stars across such vast distances is extraordinarily difficult. But even taking the lower estimate, that's 100 billion suns, each one a potential center of its own planetary system. Our sun sits about 26,000 light-years from the galactic center, in what astronomers call the Orion Arm, a minor spiral arm between two larger ones. We're not in the dense, crowded center where stars pack closely together and the supermassive black hole lurks, nor are we in the sparse outer regions where stars thin out and the galaxy fades into the darkness between galaxies. We're in a comfortable suburb where stars are spaced reasonably far apart, light years between neighbors, and conditions are relatively stable. The sun orbits the galactic center at about 15,000 miles per hour, taking approximately 225 million years to complete one orbit, a galactic year. The last time the sun was at this position in its orbit, dinosaurs hadn't yet evolved on Earth. By the next time it returns here, who knows what will have become of humanity, of Earth, of the species that might follow us. Pulsars are neutron stars, the collapsed cores of massive stars after supernovae, that spin rapidly and emit beams of radiation from their magnetic poles. As the neutron star rotates, these beams sweep across space, like lighthouse beams sweeping across the ocean. If Earth happens to lie in the path of one of these beams, we detect a pulse of radiation each time the beam sweeps past, hence the name pulsar. Some pulsars spin hundreds of times per second. their beams flashing past with such regularity that they rival atomic clocks in precision. The fastest known pulsars rotate more than 700 times per second. Imagine that, an object containing more mass than the Sun, compressed into a sphere just 12 miles across, spinning so fast its surface moves at a significant fraction of light speed. When pulsars were first discovered in 1967 by Jocelyn Bell Burnell, the signals were so regular, so precisely timed, that astronomers briefly wondered if they might be signals from an alien civilization. They even nicknamed the first one LGM-1 for Little Green Men. But further observations showed pulsars were natural phenomena. Neutron stars whose extreme properties created these lighthouse-like beams. Pulsars gradually slow down as they lose energy, their spins decreasing over millions of years until they eventually stop pulsing and become quiet, dark neutron stars. But for now, thousands of pulsars spin throughout the galaxy, their beams sweeping endlessly through space. Cosmic timekeepers marking the seconds with precision, born of physics operating at extremes we can barely imagine. There's a star designated HD 1.0283, but commonly called the Methuselah star, that presents astronomers with a puzzle. Based on measurements of its composition and brightness, the star appears to be about 14.5 billion years old, give or take a few 100 million years. The problem? Our best estimate for the age of the universe itself is 13.8 billion years. Obviously, nothing can be older than the universe, so either the star's age is overestimated or the universe's age is underestimated, or both measurements have uncertainties that, when properly accounted for, resolve the contradiction. Current thinking leans toward the first option. The star is probably younger than initial estimates suggested, perhaps 13.5 billion years old, which fits comfortably within the universe's age when you account for measurement uncertainties. But the fact that we encountered this puzzle at all is humbling. Methuselah is one of the oldest known stars, formed when the universe was still in its infancy, before the Milky Way had fully assembled, when the cosmos was simpler, containing mostly just hydrogen and helium, with only trace amounts of heavier elements. Stars like Methuselah are called population 2 stars, ancient, metal-poor, survivors from the early universe. Studying such stars gives us a window into cosmic history, into conditions shortly after the Big Bang. They're time capsules, preserving information about the early universe in their composition and structure. And occasionally, they remind us that our measurements, precise as they are, still carry uncertainties. And sometimes those uncertainties collide with each other in ways that challenge us to refine our understanding. When a star like our Sun exhausts its hydrogen fuel, it swells into a red giant, then sheds its outer layers into space, leaving behind its dense core, a white dwarf. This remnant is roughly the size of Earth, but contains about as much mass as the Sun. Imagine compressing the Sun, massive enough that its gravity holds 8 planets in orbit, down to the size of our planet. The density becomes extraordinary. A sugar cube-sized piece of white dwarf material would weigh about 15 tons on Earth, roughly the weight of 2 elephants compressed into a 1-centimeter cube. This density is maintained by electron degeneracy pressure, a quantum mechanical effect where electrons resist being compressed into the same space, creating an outward pressure that balances gravity's inward pull. White dwarfs don't generate energy through fusion anymore. Their fusion days are over. Instead, they shine simply by radiating away their residual heat, gradually cooling over billions of years. They start out intensely hot, surface temperatures of 100,000 degrees Fahrenheit or more, glowing white or blue-white. But as they radiate heat into space, they cool, fading through yellow to red, to eventually, in the distant future, becoming black dwarfs, cold, dark remnants invisible except by their gravity. The universe isn't old enough yet for any black dwarfs to exist. Even the oldest white dwarfs are still faintly glowing. But given enough time, trillions of years, most stars in the universe will end as black dwarfs, cold cinders drifting through an increasingly dark and empty cosmos, monuments to the stars that once were. In the Eagle Nebula, about 6,500 light-years from Earth, there are 3 towering columns of gas and dust called the Pillars of Creation. These pillars are immense. Each one stretches about 5 light-years tall, roughly the distance from the Sun to the nearest star system. They're composed primarily of hydrogen gas and dust, opaque enough to block visible light from stars behind them. Inside these pillars, new stars are being born. Dense pockets of gas collapse under their own gravity, heating up until nuclear fusion ignites, and a new star blazes to life. The ultraviolet radiation from nearby hot young stars erodes the pillars from the outside, sculpting them into their distinctive shapes, like wind-carving sand dunes, except the wind is starlight and radiation, and the sand is interstellar gas. The Pillars of Creation became famous from a Hubble Space Telescope image taken in 1995, one of the most iconic astronomical photographs ever captured. The image shows the pillars in stunning detail, backlit by glowing gas, their surfaces textured with detail, knots and globules where denser material resists erosion. It's an image of both creation and destruction, stars being born while the structures that birthed them are slowly evaporated away. There's a poignant footnote to the story. Based on observations of a nearby supernova remnant, some astronomers think the pillars may have already been destroyed by a supernova shockwave about 6,000 years ago. But because the pillars are 6,500 light-years away, we wouldn't see that destruction for another 500 years. We might be looking at structures that no longer exist, preserved for us by the time it takes light to travel, like a photograph of someone long dead. In about 5 billion years, the Sun will begin to die. Having fused most of the hydrogen in its core into helium, it will start fusing hydrogen in a shell around the core. This will cause the Sun to swell enormously, expanding into a red giant, perhaps 100 times its current diameter. The surface will cool, glowing red instead of yellow, but the sheer size will make it far brighter than it is now. As the Sun expands, it will likely engulf Mercury and Venus, vaporizing them entirely. Earth's fate is less certain. Some models suggest the Sun will expand just far enough to reach Earth's orbit, while others suggest Earth might barely escape, though it would be scorched, its atmosphere stripped away, its oceans boiled into space. Either way, Earth as we know it, green and blue and alive, will be gone. If any humans still exist then, and 5 billion years is an almost inconceivably long time for any species to survive, they'll have had to leave Earth long before the Sun's transformation. Perhaps they'll watch from distant colonies as their home world dies, consumed or sterilized by the star that once nurtured it. Eventually, the Sun will shed its outer layers entirely in a planetary nebula, not an explosion like a supernova, but a gentler release, the layers drifting away, to form a colorful shell of glowing gas around the remaining core. That core will become a white dwarf, slowly cooling over billions of years, a quiet ending to a star that burned for 10 billion years. The story has a kind of poetry to it: birth, life, death, each stage governed by the same physical laws that govern everything else in the universe. Magnetars are a special type of neutron star with magnetic fields a quadrillion times stronger than Earth's. To put that in perspective, if a magnetar existed halfway between Earth and the Moon, its magnetic field would be strong enough to strip the data from every credit card on Earth, disrupt electronic devices globally, and potentially be lethal to anyone nearby by disrupting the molecular bonds in their bodies. The magnetic fields are so intense that they distort the neutron star's crust, causing starquakes, sudden rearrangements of the star's structure that release enormous bursts of X-rays and gamma rays. When this happens, the magnetar can briefly become the brightest source of X-rays in the sky, outshining everything except the sun, despite being thousands of light years away. These bursts are called soft gamma repeaters, or anomalous X-ray pulsars, and they're some of the most energetic events regularly occurring in the galaxy. In December 2004, a magnetar about 50,000 light-years away released a burst so powerful that it measurably affected Earth's upper atmosphere, causing it to swell. The energy that reached Earth in just a tenth of a second was more than our Sun emits in 150,000 years. Fortunately, magnetars are rare, only about a dozen confirmed in our galaxy, and none are close enough to pose a danger. But they represent yet another extreme in the universe's repertoire, another way that matter and energy can be organized into something strange and powerful, operating at scales and intensities that our everyday experience can scarcely comprehend. In mapping the distribution of galaxies across the universe, astronomers discovered that galaxies aren't randomly scattered, but organized into large structures, filaments, sheets, and clusters separated by vast voids. One of the largest known structures is the Sloan Great Wall, a massive concentration of galaxies stretching approximately 1.4 billion light-years across space. To grasp this scale, light, traveling at 186,082 miles per second, takes 1.4 billion years to cross from one end of this structure to the other. It contains hundreds of thousands of galaxies, each containing billions of stars. The structure is so large that it challenges some cosmological theories about how matter could have clumped together into such massive concentrations in the time since the Big Bang. The Sloan Great Wall is part of what's called the cosmic web, the large-scale structure of the universe resembling a three-dimensional spider's web, with galaxies arranged along filaments surrounding empty voids. If you could step back and view billions of light-years of space at once, you'd see this foam-like structure, with matter concentrated along the edges of vast empty bubbles. We're part of this structure too, residents of a galaxy that sits somewhere within the cosmic web, connected by gravity and large-scale flows of matter to galaxies millions of light-years away. The universe has structure on every scale: atoms, molecules, planets, stars, galaxies, clusters, superclusters, and these vast walls and filaments. Pattern within pattern, organization emerging from the simple laws of gravity and motion acting over billions of years. Stars come in different colors, and those colors tell us their surface temperatures. The hottest stars burn blue or blue-white, with surface temperatures exceeding 50,000 degrees Fahrenheit. Slightly cooler stars appear white, then yellow like our sun at about 10,000 degrees, then orange. And finally, the coolest stars glow red at around 5,000 degrees Fahrenheit. This might seem backwards. We often think of red as hot and blue as cold, from fire and ice. But in physics, color correlates with temperature in the opposite way. Hotter objects emit light at shorter wavelengths, which our eyes perceive as blue. Cooler objects emit longer wavelengths, which appear red. This relationship, called black body radiation, applies to everything that glows from its own heat. Stars, light bulb filaments, heated metal. The hottest stars, massive blue giants, burn fiercely but briefly, exhausting their fuel in just a few million years before exploding as supernovae. The coolest stars, small red dwarfs, burn so slowly and efficiently that they can last for trillions of years, far longer than the current age of the universe. In fact, no red dwarf has ever died of old age yet. The universe simply isn't old enough. Our sun, yellow and middle-aged, represents a comfortable middle ground. Not too hot, not too cool, burning steadily for billions of years, providing stable warmth to its planets. When you look at the night sky and see stars of different colors, Betelgeuse's reddish glow, Rigel's blue-white brilliance, the yellowish hue of Capella, you're seeing a temperature spectrum, a visual representation of stars at different stages of life, burning at different intensities. Globular clusters are ancient stellar cities, dense spherical collections of stars orbiting galaxies, like satellites. A typical globular cluster contains hundreds of thousands to millions of stars packed into a region just 50 to 100 light years across. That might sound spacious, but compared to the distances between stars in our neighborhood, where the nearest star to the sun is over 4 light years away, it's incredibly crowded. If Earth orbited a star in the dense core of a globular cluster, the night sky would be spectacular beyond imagination. Thousands of stars would shine brighter than Venus appears from Earth. There would be no true darkness, just a perpetual twilight even at midnight, the sky glowing with countless brilliant points of light. You could read by starlight alone. Globular clusters are old, among the oldest objects in the universe. Most formed between 10 and 13 billion years ago, when the universe was young and galaxies were still assembling. The stars in globular clusters are population 2 stars, metal poor because they formed before many generations of supernovae had enriched the cosmos with heavier elements. They're survivors from the ancient past, time capsules preserving conditions from the early universe. Our Milky Way has about 150 known globular clusters orbiting in a vast spherical halo around the galactic disk. They move in highly elliptical orbits, sometimes plunging through the disk, other times swinging far out into the galactic halo, taking hundreds of millions of years to complete one orbit. They're gravitationally bound to the galaxy but remain distinct, their stars held together by their own mutual gravity, resistant to being torn apart by the galaxy's tidal forces. They'll outlive most other structures, these ancient clusters, orbiting long after the spiral arms have faded and the galaxy has settled into old age. On July 4th, 1054 AD, Chinese astronomers recorded the appearance of a guest star in the constellation Taurus. This new star was bright enough to be visible during the day for several weeks, then gradually faded over the following months, until it disappeared from naked eye view. What they witnessed was a supernova, a massive star exploding just 6 to 500 light years from Earth. Today we can see the remnant of that explosion, the Crab Nebula, an expanding cloud of gas and debris still racing outward from the site of the explosion. The nebula is about 11 light years across now, and growing at roughly 3 million miles per hour. At the center sits a pulsar, the collapsed core of the original star, spinning 30 times per second, powering the nebula with energy from its rotation. The Crab Nebula glows in complex filamentary structures, wisps and tendrils of gas heated to millions of degrees, threaded with magnetic fields, illuminated by synchrotron radiation from electrons spiraling at near light speed. Hubble images show it in exquisite detail, a tapestry of colors representing different elements: oxygen, sulfur, hydrogen, each glowing at characteristic wavelengths. What's remarkable is the connection across time. Those Chinese astronomers saw the initial explosion, the moment of stellar death. We see the aftermath, still expanding, still evolving, nearly 1,000 years later. And if we wait another 1,000 years, the nebula will have grown larger. Its details changed, but still recognizably the same structure. The frozen explosion spreading slowly into interstellar space. It's a reminder that even violent cosmic events unfold slowly on human timescales, that the universe's dramas play out over centuries and millennia, patient and unhurried. When we think of stars, we often picture solitary objects like our sun, alone except for its retinue of planets. But actually, binary star systems, two stars orbiting each other, are more common than single stars. Some estimates suggest that more than half of all stars exist in binary or multiple star systems, bound together by gravity, waltzing around their common center of mass. These systems come in many varieties. Some binaries are so close that they nearly touch, transferring material between them, their outer atmospheres distorted by mutual tidal forces. Others are separated by distances comparable to planetary orbits, each star maintaining its own space while remaining gravitationally bound to its partner. Still others are so widely separated that they take thousands of years to complete one orbit, their connection barely apparent except through careful observation. If Earth orbited in a close binary system, we might experience constant daylight, with one sun setting as the other rises, or periods of double shadows when both suns shine in the sky simultaneously. The seasons would be complex, influenced by which star Earth was closer to at any given time. And the night sky, those rare moments when both suns were below the horizon, would be brief and precious. Binary stars can have dramatic fates. If one star is more massive, it will die first, potentially becoming a white dwarf or neutron star. Then, if the companion later swells into a red giant, material can flow from the giant onto the compact remnant, creating novae or even triggering type Ia supernovae. Explosions so consistent in brightness that astronomers use them as standard candles to measure cosmic distances. Even in death, binary stars remain connected, their fates intertwined. At the center of the Milky Way, about 26,000 light years from Earth, lies a region of extraordinary activity and density. Stars crowd together there, packed thousands of times more densely than in our neighborhood. And at the very heart of this stellar congregation sits Sagittarius A, pronounced Sagittarius A star, a supermassive black hole containing about 4 million times the mass of our Sun. We can't see Sagittarius A or directly. It's a black hole, and black holes don't emit light. But we can observe its effects on nearby stars. Astronomers have tracked individual stars orbiting the black hole, some swooping in so close that they reach speeds of several percent of light speed. These orbital motions prove conclusively that something immensely massive and compact sits there, invisible but undeniable. The galactic center is hidden from optical view by thick clouds of dust that absorb visible light. But infrared and radio waves can penetrate the dust, allowing us to peer into this crowded, energetic region. What we see is chaos, stars whipping around the central black hole, clouds of hot gas, magnetic fields, and occasional flares of radiation when material falls toward the black hole and heats up before crossing the event horizon. If you could somehow visit the galactic center, protected from the radiation and heat, the night sky would be extraordinary. Stars would be so numerous and bright that there would be no true darkness, the sky glowing with thousands of brilliant suns. But it would also be a dangerous place, with intense radiation, strong magnetic fields, and the gravitational influence of the black hole warping space nearby. It's magnificent and hostile, the violent, crowded heart of our galaxy. Most galaxies form new stars at a relatively steady pace. The Milky Way, for example, creates about 1 or 2 new stars per year, enough to maintain its population as old stars die, but not dramatically changing the galaxy's character. But some galaxies, called starburst galaxies, form stars hundreds or even thousands of times faster, creating new suns at a frenzied, unsustainable rate. What causes this explosion of star formation? Usually, it's triggered by galactic collisions or close encounters. When 2 galaxies pass near each other or merge, their gravitational interactions compress gas clouds, triggering massive waves of star formation. Billions of new stars can form in just a few million years, lighting up the galaxy with brilliant, blue-white light from hot, massive, short-lived stars. This frenzy can't last. The galaxy exhausts its gas supply, using up the raw material for star formation far faster than it's replenished. Eventually, the starburst fades, leaving behind a galaxy with many young stars, but depleted gas reserves, unable to sustain further rapid star formation. The galaxy enters a quieter phase, burning through the stars it created during its brief period of excess. Starburst galaxies are beautiful, intensely bright, glowing with the combined light of billions of young stars, often featuring complex structures and dust lanes where star formation continues. But they're also temporary phenomena, snapshots of galaxies caught in unusual circumstances, driven by events that are dramatic but brief by cosmic standards. They remind us that galaxies, like stars, have active periods and quiet periods, bursts of activity followed by long stretches of relative calm. Space is cold. The cosmic microwave background radiation that fills the universe has a temperature of about 2.7 Kelvin, or roughly 455 degrees Fahrenheit. That's close to absolute zero, the coldest temperature possible, where molecular motion nearly stops. But there's one place in the universe that's even colder: the Boomerang Nebula, about 5,000 light-years from Earth. The Boomerang Nebula is a planetary nebula, the shell of gas expelled by a dying sun-like star. But unlike most planetary nebulae, which are heated by ultraviolet radiation from the central star, the Boomerang Nebula is cooling. The gas is expanding outward so rapidly, about 370 miles per hour, that it's cooling itself through expansion, similar to how compressed air gets cold when you release it from a spray can. The measured temperature is about 1 Kelvin, or 458 degrees Fahrenheit, just 1 degree above absolute zero, colder than the background temperature of space itself. It's the coldest known natural place in the universe, a small region where the laws of thermodynamics have conspired to create conditions colder than anywhere else nature provides. Of course, laboratories on Earth have achieved even colder temperatures, cooling atoms to billionths of a degree above absolute zero. But the Boomerang Nebula is the coldest place that exists naturally, without human intervention. It won't stay that cold forever. Eventually, the gas will disperse, mix with warmer interstellar material, and fade away. But for now, it holds the title, a frigid bubble in the cosmos, colder than the void itself. Quasars, short for quasi-stellar radio sources, were discovered in the 1960s as mysterious objects that looked like stars through telescopes, but emitted far more energy than any star could produce. They puzzled astronomers for years until the realization hit. Quasars are not stars at all, but the intensely bright centers of distant galaxies, powered by supermassive black holes consuming material at enormous rates. A single quasar can outshine all the stars in its host galaxy combined. Hundreds of billions of stars dimmed to insignificance by the blazing light from the galactic core. The black hole at the center pulls in gas and dust, which forms a swirling accretion disk around it. As material spirals inward, friction heats it to millions of degrees, causing it to radiate intensely across the electromagnetic spectrum before finally crossing the event horizon and disappearing. Quasars are so bright they can be seen from billions of light years away, from a time when the universe was young. Most quasars existed in the early universe, when galaxies were forming and merging frequently, providing abundant fuel for their central black holes. Today, quasars are rare. Most galaxies, including our own, have quieter central black holes that aren't actively consuming large amounts of material. When we observe distant quasars, we're looking back in time, seeing the universe as it was billions of years ago, when galaxies were more violent, more active, less settled. The light we detect left those quasars when the universe was young, traveling for eons across expanding space to finally reach our telescopes, carrying information about cosmic conditions long before Earth existed. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, detected a persistent noise in their antenna that they couldn't explain. No matter where they pointed the antenna, no matter what time of day or year, the noise remained. A faint hiss of radio waves coming equally from all directions. They even checked for pigeon droppings in the antenna, thinking that might be the source. It wasn't. What they'd discovered was the cosmic microwave background, the afterglow of the Big Bang itself. When the universe was about 380,000 years old, it had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, free electrons scattered light constantly, making the universe opaque like a thick fog. But once atoms formed, light could travel freely. The universe became transparent, and that first light has been traveling through space ever since. As the universe expanded, that light stretched to longer wavelengths, shifting from visible light to infrared to microwaves. Today, it fills the entire sky with faint microwave radiation at a temperature of 2.7 Kelvin, the cooled remnant of the hot, dense early universe. When you see static on an old television with no signal, about 1% of that visual noise comes from the cosmic microwave background, ancient light from the beginning of time. This radiation is remarkably uniform, but contains tiny variations, temperature differences of about 1 part in 100,000, that represent the seeds of all structure in the universe. Slightly denser regions eventually collapsed to form galaxies, stars, planets. We exist because of those tiny fluctuations, imprinted in the cosmic background radiation 13.8 billion years ago. When you look at photos of the Milky Way stretching across the sky, you might notice dark patches, regions where stars seem absent, where the bright band of the galaxy appears to have holes. These aren't actual voids, but dark nebulae, dense clouds of gas and dust so thick they block the light from stars behind them. The most famous dark nebula is the Horsehead Nebula in Orion, which appears as a dark silhouette shaped like a horse's head against a background of glowing hydrogen gas. Another striking example is the Coalsack Nebula, visible from the southern hemisphere as a dark patch in the Milky Way. These clouds appear dark not because they lack stars, but because the dust particles within them absorb visible light, preventing it from reaching our eyes. But if you observe dark nebulae in infrared wavelengths, which can penetrate dust more easily, you often find stars forming inside, newborn suns hidden from optical view, cocooned in the very clouds from which they formed. The darkness is temporary. Eventually, stellar winds and radiation from newly formed stars will blow away or evaporate the surrounding dust, revealing the star cluster within. There's something beautifully poetic about dark nebulae. They appear as absence, as empty holes in the stellar tapestry, but they're actually regions of presence, of densely packed matter, nurseries where stars are being born in secret. What looks like nothing is actually something, hidden from view, waiting to be revealed when the dust finally clears. The Tarantula Nebula, located in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, is one of the most active star-forming regions known. It's about 160,000 light-years away, much farther than most nebulae we observe, yet it's still visible to the naked eye from the southern hemisphere as a faint, fuzzy patch. That visibility, despite its distance, tells you how bright it must be. The nebula spans about 1,000 light-years across and contains enough gas to form hundreds of thousands of stars. At its core is a cluster of massive, hot stars, some of the largest and most luminous stars known, burning fiercely and pouring ultraviolet radiation into the surrounding gas, causing it to glow. These stars are so massive and bright that if the Tarantula Nebula were as close as the Orion Nebula, only about 2,300 light-years away, it would cast shadows on Earth at night and be visible during the day. The nebula gets its name from its spidery, filamentary appearance, tendrils of glowing gas extending outward from the bright central region, resembling a tarantula's legs. These structures are sculpted by stellar winds and radiation, the same forces that create the pillars of creation and other nebular features, but on a grander scale. The Tarantula Nebula represents star formation at its most intense and dramatic, a stellar nursery producing massive stars that will live fast and die young in spectacular supernovae, enriching the surrounding space with heavy elements and possibly triggering new waves of star formation. Its creation in overdrive, a glimpse of how galaxies build their stellar populations. Einstein's general relativity predicts that massive objects bend space itself, and light traveling through bent space follows curved paths. This means that a massive object, a galaxy cluster, even a star, can act like a lens, bending light from objects behind it. This phenomenon is called gravitational lensing, and it's been confirmed countless times through astronomical observations. When a distant galaxy lies almost directly behind a massive galaxy cluster, from our perspective, the cluster's gravity bends the distant galaxy's light around it, often creating multiple distorted images, sometimes arcs, sometimes complete rings called Einstein rings. The background galaxy appears stretched, magnified, multiplied, its light bent around the intervening mass like light through a glass lens. Astronomers use gravitational lensing as a tool. By studying how light is bent, they can map the distribution of mass in the lensing object, including dark matter that doesn't emit light but still has gravitational effects. Lensing also magnifies distant objects, allowing us to see galaxies that would otherwise be too faint to detect. The universe providing us with a natural telescope. One of the most striking examples is the Hubble Deep Field images, which show distant galaxies lensed and magnified by foreground galaxy clusters. Some of these galaxies are so far away that we're seeing them as they appeared just a few 100 million years after the Big Bang, their light traveling for over 13 billion years before reaching us, bent and magnified along the way by the gravity of intervening matter. Gravitational lensing is a beautiful confirmation of Einstein's predictions. Space really is curved by mass. Light really does follow that curvature. And it's practical too, extending our vision across cosmic distances, revealing structures we couldn't otherwise see, allowing us to weigh the universe by watching how it bends light. Not all planets orbit stars. Some wander through the galaxy alone, dark and cold, ejected from their home systems, or perhaps formed in isolation. These are rogue planets, world-sized objects drifting through interstellar space, unbound to any star, following their own orbits around the galactic center. How do planets become rogues? Most are likely ejected during the chaotic early history of planetary systems. When multiple planets form, their gravitational interactions can be unstable. Close encounters can fling planets outward, sometimes with enough velocity to escape the star's gravity entirely. Suddenly unmoored, the planet sails off into the darkness, its surface rapidly cooling without a sun's warmth. Rogue planets are difficult to detect because they don't reflect starlight. They're invisible except when they pass in front of a background star, briefly lensing its light, or when we detect their faint infrared glow, residual heat from their formation slowly radiating into space. But statistical estimates suggest there might be billions of rogue planets in our galaxy, possibly outnumbering stars. Imagine one of these worlds. Perhaps it once had warmth, liquid water, maybe even life when it orbited a star. Then some gravitational catastrophe sent it flying into the void. Its oceans would freeze. Its atmosphere might condense as snow on the surface, and it would drift through eternal night, seeing stars but never feeling their warmth. It's a melancholic image, these orphaned worlds wandering the galaxy, remnants of planetary systems that failed to remain stable. Some rogue planets might still harbor life, improbably enough. If a planet is massive enough to retain internal heat from radioactive decay, Subsurface oceans might persist for billions of years beneath frozen surfaces, similar to the moon's Europa or Enceladus. Life in such oceans would know only darkness, warmed by geology, not astronomy, surviving without sunlight in an isolated aquatic world drifting through the cosmos. If you could step back far enough to view hundreds of millions or billions of light years of space at once, you'd see that galaxies aren't randomly scattered, but organized into a vast structure called the cosmic web. Galaxies cluster along filaments, long, thread-like concentrations of matter, surrounding enormous voids where few galaxies exist. It looks remarkably like a three-dimensional spider's web, or like the foam in a bathtub, with matter concentrated along the edges of bubbles. This structure emerged from tiny density fluctuations in the early universe. Slightly denser regions attracted more matter through gravity, growing denser still, while less dense regions emptied out as their matter was pulled toward the overdense areas. Over billions of years, this process created the filamentary structure we see today. The filaments are immense, stretching hundreds of millions of light years, and contain most of the universe's ordinary matter, including gas that has never formed stars. The voids between them can be equally enormous, containing very few galaxies, mostly empty space. Our Milky Way sits within a filament, part of a larger structure called the Laniakea supercluster, which contains about 100,000 galaxies, all slowly flowing along gravitational currents shaped by the cosmic web's structure. This large-scale organization is one of the universe's most striking features. From atoms to planets to stars to galaxies to superclusters to the cosmic web, pattern upon pattern, structure at every scale, each level of organization emerging from simpler laws of physics acting over time. The universe is not chaotic but structured, ordered by gravity into hierarchies of increasing scale, revealing an elegant architecture when viewed from the right perspective. Most stars orbit the galactic center at relatively sedate speeds. Our sun travels about 15,000 miles per hour, taking 225 million years to complete one orbit. But scattered throughout the galaxy are hypervelocity stars. Stars moving so fast, they're escaping the Milky Way entirely, flying outward at millions of miles per hour, destined to spend eternity wandering intergalactic space. How do stars reach such extreme speeds? The leading theory involves close encounters with Sagittarius A, the supermassive black hole at the galactic center. If a binary star system ventures too close, the black hole's gravity can tear the pair apart, capturing one star while flinging the other outward at tremendous speed, like a gravitational slingshot. The escaping star, accelerated to several hundred kilometers per second, races away from the galaxy. These stars are traveling fast enough to escape not just the galactic disk, but the galaxy's entire gravitational well. They'll coast through the space between galaxies, watching the Milky Way shrink behind them, seeing it eventually as just another distant spiral, one of many. If they pass close to other galaxies, they might be captured by those galaxies' gravity, finding a new home. But more likely, they'll wander the cosmic voids forever, solitary exiles. There's something poignant about hypervelocity stars, cast out by a chance encounter, condemned to isolation, forever separated from the galactic community of billions of stars. They're cosmic nomads, and any planets orbiting them would see the night sky gradually change as nearby stars shift position. The familiar constellations slowly dissolving as the star flies farther from its birthplace, heading toward regions no star has visited before. For most of the 20th century, astronomers assumed the universe's expansion was slowing down. Gravity should pull galaxies toward each other, they reasoned, gradually decelerating the expansion that began with the Big Bang. The question was whether gravity would eventually halt the expansion, causing the universe to collapse back in a big crunch, or whether expansion would continue forever, but gradually slow to near zero speed. Then in 1998, two independent teams studying distant supernovae made a shocking discovery. The universe's expansion isn't slowing down, it's speeding up. Galaxies aren't just moving apart, they're moving apart faster and faster. Something is pushing space to expand at an accelerating rate. This discovery was so unexpected that astronomers initially doubted it, but repeated observations confirmed the results. The universe's expansion is accelerating, driven by something we call dark energy, a mysterious form of energy that fills space and exerts a kind of negative pressure, pushing space apart. Dark energy accounts for about 68% of the universe's total energy content, yet we don't know what it is, what causes it, or why it has the strength it does. The implications are profound. If acceleration continues, the universe will expand forever, eventually reaching a state where galaxies beyond our local group recede so fast their light can never reach us. The observable universe will shrink, other galaxies fading from view one by one as they cross the cosmic horizon. Trillions of years from now, any astronomers in the Milky Way would see a dark, empty sky, unaware that billions of other galaxies exist beyond their vision, racing away into the darkness. Astronomers noticed something odd when they measured how fast galaxies rotate. The outer edges of spiral galaxies were rotating as fast as the inner regions, which shouldn't happen according to the visible matter's gravitational pull. Based on the stars and gas we can see, outer regions should rotate much slower. Otherwise, they should fly apart. But they don't. The conclusion was unavoidable. Galaxies contain far more mass than we can see, some form of matter that doesn't emit, absorb, or reflect light. We call it dark matter, and it apparently makes up about 27% of the universe's total mass energy content, 5 times more than ordinary matter, the stuff that makes stars, planets, and people. We detect dark matter only through its gravitational effects, how it influences galaxy rotation, how it bends light through gravitational lensing, how it affects the cosmic microwave background's temperature fluctuations. But we don't know what dark matter is made of. It's not any particle we've identified in laboratories. The leading candidates are exotic particles predicted by theories extending beyond the standard model of particle physics. WIMPs, weakly interacting massive particles, axions, or perhaps something stranger. Experiments around the world are searching for dark matter particles, trying to detect them directly as they pass through Earth. So far, no confirmed detection. Dark matter remains mysterious, invisible, known only by its gravitational pull on visible matter. It's humbling. Most of the matter in the universe is made of something we don't understand, something we can't see, something that exists all around us and through us, but that we've never directly observed. The universe holds its secrets close. Our galaxy, along with hundreds of thousands of neighboring galaxies, is being pulled toward something. This gravitational anomaly, called the Great Attractor, lies about 250 million light years away, and it's pulling our entire corner of the universe toward it at about 1.3 million miles per hour. We can't see the Great Attractor directly because it lies in the zone of avoidance, a direction obscured by the Milky Way's own disk, where thick clouds of dust and stars block our view of distant objects. But we can detect its presence by measuring the peculiar velocities of galaxies, their motion toward or away from us that deviates from the smooth expansion of the universe. Those measurements reveal a massive concentration of matter pulling us toward it. Recent observations suggest the Great Attractor itself might be influenced by an even larger structure, the Shapley supercluster, the largest concentration of galaxies in the nearby universe, containing thousands of galaxies with combined mass tens of thousands of times greater than the Milky Way. Together, these massive structures create currents in space-time, pulling galaxies along like rivers flowing toward the ocean. It's disconcerting in a way. We tend to think of the universe's expansion as smooth and uniform, with galaxies moving apart evenly. But locally, gravity creates flows and currents, concentrations and voids. We're not just expanding away from other galaxies, we're also being pulled toward concentrations of mass, participating in motions shaped by structure on scales far larger than our galaxy. We're swimmers in a cosmic current, flowing toward a destination we can't quite see. Every second, countless high-energy particles called cosmic rays bombard Earth from space. Most are protons, hydrogen nuclei, traveling at nearly the speed of light, though some are heavier atomic nuclei or electrons. They slam into Earth's upper atmosphere, creating cascades of secondary particles that shower down through the air. Some of these particles reach the surface, and some pass right through you. Cosmic rays originate from violent events across the galaxy and beyond: supernova explosions, pulsars, black holes, possibly even from outside our galaxy in distant active galactic nuclei. They've been accelerated to tremendous energies by shock waves and magnetic fields, flung through space at relativistic speeds, traveling for thousands or millions of years before reaching Earth. When high-energy cosmic rays hit your body, they can damage DNA, potentially causing mutations. Earth's atmosphere shields us from most cosmic rays. The air molecules absorb and scatter them before they reach the surface. But astronauts in space or on the moon have minimal protection, and cosmic ray exposure is one of the significant health risks of long-duration spaceflight. The most energetic cosmic rays ever detected carry energies equivalent to a baseball thrown at 60 miles per hour. Except all that energy is contained in a single subatomic particle. Where such particles get their energy remains mysterious. They're called "oh my God" particles, because their existence seems to violate theoretical limits on how energetic particles can be. They're messengers from cosmic violence we don't fully understand. Bullets fired by the universe's most extreme engines, arriving at Earth to tell us stories of catastrophes in distant galaxies. The Hercules Corona Borealis Great Wall might be the largest structure in the observable universe. This concentration of galaxy clusters spans approximately 10 billion light-years, roughly 10% of the observable universe's diameter. Light takes 10 billion years to cross it, meaning we see different parts of the structure at vastly different cosmic ages. The structure's existence is somewhat controversial. It was identified by mapping gamma-ray bursts, which tend to occur in regions of higher galaxy density. But some astronomers question whether it's a real, coherent structure, or just a statistical fluctuation, a pattern that emerges from random clustering but doesn't represent a physically connected entity. If it is real, it challenges some cosmological assumptions. The cosmological principle states that on large enough scales, the universe should be roughly uniform. No structure should be so large that it dominates the cosmic landscape. But the Hercules Corona Borealis Great Wall, spanning 10 billion light years, approaches the scale where the universe should start looking smooth and uniform. Its existence suggests that cosmic structure might extend to larger scales than theories predicted. Whether it's a true structure or a statistical anomaly, the possible existence of something so vast is dizzying. 10 billion light years of concentrated galaxies, a wall of matter stretching across a significant fraction of the observable universe, dwarfing even the Sloan Great Wall. If you could somehow travel along its length at the speed of light, you'd age 10 billion years before reaching the other end, watching the universe evolve around you as galaxies formed, stars lived and died, and cosmic expansion stretched space itself. The Big Bang model explains much about the universe's history, but it left some puzzles. Why is the universe so uniform? The cosmic microwave background has almost the same temperature in all directions, despite regions of space that were never in contact with each other and couldn't have exchanged heat. Why is the universe's geometry so flat, so precisely balanced between expanding forever and collapsing? In 1981, physicist Alan Guth proposed cosmic inflation, a brief period during the universe's first fraction of a second when space expanded exponentially fast, far faster than the speed of light. In less than a trillionth of a second, the universe inflated from smaller than a proton to larger than a grapefruit, possibly much larger. This stupendous expansion stretched away any initial irregularities, leaving the universe remarkably smooth and flat. Inflation solves several problems elegantly. Regions that seem disconnected now were actually in contact before inflation, explaining the universe's uniformity. The exponential expansion flattened space like stretching a balloon's surface until it appears flat, explaining the universe's geometry. And quantum fluctuations during inflation, stretched to cosmic scales, seeded the density variations that eventually became galaxies and clusters. The evidence for inflation is compelling but indirect. Patterns in the cosmic microwave background match inflation's predictions remarkably well. But we still don't know what caused inflation, what field or force drove that exponential expansion, or why it stopped after such a brief moment. Inflation remains one of cosmology's most successful yet mysterious ideas. Explanation that works beautifully, but raises deeper questions about the universe's first moments. Black holes come in different sizes. Stellar mass black holes form when massive stars collapse, typically containing about 5 to 100 times the sun's mass. Supermassive black holes lurk at galaxy centers, containing millions to billions of solar masses. But there should be something in between, intermediate mass black holes, perhaps 100 to 100,000 solar masses. And yet, for years, we couldn't find clear evidence they existed. This gap in the black hole population puzzled astronomers. How do supermassive black holes get so massive? They might grow by consuming gas and merging with other black holes, but starting from stellar mass black holes and growing to billions of solar masses in the time available seems difficult. Intermediate mass black holes could be the missing link. Seeds that formed early in the universe's history and grew into the supermassive monsters we see today. Recent observations have found candidates. Some globular clusters show evidence of intermediate mass black holes at their centers, inferred from the motions of nearby stars. Gravitational wave detectors have recorded mergers that produced black holes in the intermediate mass range. The evidence is mounting, though each candidate requires careful verification. If intermediate mass black holes exist in significant numbers, they might help explain how supermassive black holes formed so quickly. Some existed when the universe was less than 1 billion years old, which seems too short a time to grow from stellar mass seeds. Perhaps intermediate mass black holes formed through different mechanisms, collisions of massive stars in dense clusters, or direct collapse of gas clouds in the early universe, providing the massive seeds that became the supermassive black holes we observe today. When we say the universe is expanding, it's natural to picture an explosion, matter flying outward from some central point into empty space beyond, like a bomb detonating. But that's not what's happening. The universe has no center and no edge. Every point in space can consider itself the center of the expansion. This is because space itself is expanding. Galaxies aren't moving through space. Space between galaxies is growing, carrying them apart. Imagine dots drawn on a balloon. As you inflate the balloon, the dots move apart, but not because they're traveling across the balloon surface. The surface itself is expanding, and the dots are carried along. Each dot sees all other dots moving away, and from any dot's perspective, it appears to be at the center of the expansion. The same applies to the universe in 3 dimensions. Space is stretching everywhere simultaneously. There's no special location from which expansion emanates, no boundary where expansion stops. The universe is either infinite, extending forever in all directions, or finite but unbounded, like the surface of a sphere that curves back on itself without having an edge. This means there's no outside the universe in the usual sense. The universe isn't expanding into anything. There's no pre-existing space for it to expand into. Space itself is what's expanding, creating more distance between galaxies. It's a concept that challenges our intuition because we're used to things expanding into empty space. But the universe's expansion is fundamentally different, stranger, more abstract. Most black holes form from collapsing stars, but there's a theoretical possibility of primordial black holes that formed in the first moments after the Big Bang from extremely dense pockets of matter. In the early universe's intense heat and pressure, if matter clumped densely enough in certain regions, it might have collapsed directly into black holes without needing stellar processes. These primordial black holes could range dramatically in mass, from microscopic, containing less mass than a mountain, but smaller than an atom, to thousands of solar masses. The smaller ones would have evaporated by now through Hawking radiation, but intermediate and larger ones might still exist, scattered throughout the universe. Here's where it gets interesting. Primordial black holes might account for some or all of dark matter. They would be massive, affecting galaxy rotation and gravitational lensing, but invisible since they don't emit light. Searches for primordial black holes look for gravitational lensing events, brief brightening of distant stars as a black hole passes in front, and for gravitational waves from primordial black hole mergers. So far, evidence is limited. Some gravitational wave detections might involve primordial black holes, but confirming this is difficult. If primordial black holes make up dark matter, they'd need a specific mass range to match observations. Too small and they'd have evaporated. Too large and we'd have detected their gravitational effects already. It's an elegant solution to dark matter's mystery, but whether nature chose this solution remains uncertain. The universe is 13.8 billion years old, so you might think the observable universe, the portion from which light has had time to reach us, would be 13.8 billion light years in radius. But it's actually much larger, about 46.5 billion light years in radius, making the observable universe approximately 93 billion light years across. Why the discrepancy? Because space itself has been expanding while light traveled toward us. Imagine a galaxy emitting light when the universe was just 1 billion years old. That light has been traveling for 12.8 billion years to reach us. But during those 12.8 billion years, space expanded, stretching the distance between us and that galaxy. The galaxy is now much farther away than the light's travel time suggests, about 36 billion light years distant, in fact. So the observable universe is a sphere centered on Earth, extending 46.5 billion light years in every direction, encompassing everything from which light has had time to reach us since the Big Bang. Beyond this horizon lie regions whose light hasn't reached us yet, not because they're inherently unreachable, but because the universe hasn't been around long enough for their light to arrive. And the universe beyond the observable portion? It might be infinite, filled with galaxies we'll never see. Or it might be finite, curving back on itself in ways we can't observe. The observable universe is just the part we can see, a local bubble in what might be an endless cosmos, or a closed system we're trapped within. We don't know which, and we might never know. Gamma-ray bursts are the most energetic explosions in the universe, brief flashes of gamma rays lasting from milliseconds to several minutes, releasing more energy in seconds than the sun will emit in its entire 10 billion year lifetime. They're detected from distant galaxies, billions of light years away, yet still bright enough to be observed from Earth despite the immense distance. There are two main types: short gamma-ray bursts lasting less than 2 seconds, likely result from colliding neutron stars. Two ultra-dense stellar remnants spiraling together and merging in a catastrophic collision that releases gravitational waves and a burst of gamma rays. Long gamma-ray bursts, lasting more than 2 seconds, probably come from collapsing massive stars, hypernovae, more energetic than typical supernovae, where the collapsing core forms a black hole surrounded by an accretion disk that launches jets of material at nearly light speed. When these jets point toward Earth, we see the gamma-ray burst, a concentrated beam of energy so intense it briefly outshines everything else in the gamma-ray sky. If a gamma-ray burst occurred in our galaxy, aimed at Earth from within a few thousand light years, it could strip away the ozone layer, exposing the surface to harmful ultraviolet radiation, potentially causing mass extinctions. Fortunately, gamma-ray bursts are rare, and the odds of one occurring nearby and aimed at us are extremely small. but they remind us that the universe contains violent events of almost incomprehensible energy, explosions that dwarf anything humanity could produce, moments when dying stars release energies that briefly match the output of entire galaxies. There's a fundamental limit to how far we can see in the universe, not because our telescopes aren't powerful enough, but because of the universe's finite age and expansion. The cosmic horizon marks the farthest distance light could have traveled since the Big Bang. Beyond this boundary, light hasn't had enough time to reach us yet. But there's a more absolute horizon too. Due to the universe's accelerating expansion, there are galaxies beyond a certain distance, currently about 16 billion light-years away, that are receding faster than light can travel toward us. Light from these galaxies will never reach Earth, no matter how long we wait. They're beyond what's called the event horizon of the observable universe, forever separated from us by expanding space. As the universe continues expanding and acceleration continues, this horizon will move closer. Galaxies currently visible will cross the horizon and fade from view as they recede beyond the point where their light can reach us. Eventually, only our local group of gravitationally bound galaxies will remain observable. Everything else will have receded beyond the horizon, their light redshifted into oblivion. This means the observable universe is shrinking in a sense. We can see more of the universe's past as light from increasingly distant galaxies arrives. But we'll see less of the universe's future as galaxies cross the horizon. Future astronomers, trillions of years from now, might observe a dark, lonely cosmos containing only their local galaxy group, unaware that billions of other galaxies exist beyond their vision, forever out of reach. Approach a black hole's event horizon, the boundary beyond which nothing can escape, and time behaves strangely. From the perspective of someone falling toward the black hole, everything seems normal. Time passes regularly, and they cross the event horizon in finite time, plunging toward the singularity at the center. But to someone watching from a safe distance, something different happens. As the falling person approaches the event horizon, they appear to slow down. Time dilation becomes more extreme, closer to the horizon. The falling person's movements slow, their signals redshift, their clock appears to tick slower and slower. At the event horizon itself, time appears to stop completely from the distant observer's perspective. The falling person seems frozen there, never quite crossing, forever suspended at the boundary. This isn't an illusion. It's a genuine consequence of how gravity warps space-time. There's no universal now that everyone agrees on. The falling person's experience and the distant observer's observations are both valid, just incompatible. Different reference frames experience time differently near black holes. This has a strange implication. From the distant universe's perspective, nothing ever falls into a black hole. Everything accumulates at the event horizon, frozen in time. But from the perspective of the infalling matter, crossing happens quickly. Both descriptions are correct, just in different reference frames. Time near a black hole becomes relative in ways our everyday intuition can't grasp, stretched and distorted by gravity's intense curvature of space-time. Stephen Hawking predicted that black holes aren't completely black. They should emit faint radiation and gradually evaporate over immense timescales. This seems paradoxical since nothing can escape from inside a black hole. But Hawking radiation arises from quantum effects at the event horizon. In quantum mechanics, the vacuum isn't truly empty, but seethes with virtual particle-antiparticle pairs that constantly appear and annihilate. Near a black hole's event horizon, sometimes one particle of a pair falls into the black hole, while the other escapes. To an outside observer, it appears the black hole emitted a particle. This process carries away energy, causing the black hole to slowly lose mass. The radiation is incredibly faint for stellar mass or larger black holes. The temperature is inversely proportional to the black hole's mass. So massive black holes are extremely cold, radiating less than the cosmic microwave background. But as a black hole evaporates and becomes smaller, it gets hotter, radiating faster, eventually ending in a rapid burst of energy as the last bit of mass converts to radiation. For a black hole with the sun's mass, complete evaporation would take about 1067 years, far, far longer than the universe's current age. But smaller primordial black holes would evaporate faster. Those with initial masses around 1 billion tons would just be evaporating now, 13.8 billion years after the Big Bang. We've never detected such evaporation events, though astronomers search for the characteristic gamma-ray signatures they'd produce. The vacuum of space isn't truly empty. According to quantum mechanics, the uncertainty principle means that even in the perfect vacuum, quantum fields fluctuate. Virtual particle-antiparticle pairs constantly appear and annihilate on timescales so short we can't directly observe them. Particles borrowing energy from uncertainty, existing briefly, then disappearing as they return the borrowed energy. This quantum foam operates at scales far below what we can measure. The Planck length, about 10⁻³ to 35 meters, where quantum effects and gravity become equally important, and our current theories break down. At these scales, space-time itself might fluctuate, becoming a seething chaos of appearing and disappearing geometries, wormholes forming and vanishing, space and time losing their familiar continuous character. These fluctuations have real, measurable consequences. The Casimir effect, for instance, arises from vacuum fluctuations. Place two metal plates very close together in a vacuum, and they attract each other because fewer virtual particles can exist in the narrow gap than outside, creating a pressure difference. This has been measured in laboratories, confirming that vacuum fluctuations are real. Quantum fluctuations might also have cosmic significance. During cosmic inflation, quantum fluctuations in the inflaton field, whatever field drove inflation, were stretched to enormous scales, becoming the seeds of galaxies and large-scale structure. The tiny variations in the cosmic microwave background, representing density differences that eventually grew into galaxies, might trace back to quantum fluctuations magnified to cosmic proportions. Everything we see in this view originated from quantum uncertainty in the universe's first moments. Cosmic strings are hypothetical defects in space-time, one-dimensional cracks in the fabric of the universe, like the cracks that form when water freezes. As the early universe cooled and underwent phase transitions, moments when the fundamental forces separated from their unified state, imperfections might have formed, leaving behind these topological defects. A cosmic string would be thinner than an atomic nucleus, but could stretch across the entire observable universe. Despite being microscopically thin, cosmic strings would be tremendously massive. A loop of cosmic string just a few miles across might contain as much mass as Earth. Their immense mass concentrated in such a tiny volume would make them gravitationally significant, warping space-time around them. If cosmic strings exist, they would create distinctive observational signatures. They'd gravitationally lens light, creating double images of distant objects. Oscillating cosmic string loops would emit gravitational waves. Cosmic strings moving through space might leave wakes of slightly enhanced density, possibly seeding galaxy formation. Astronomers search for these signatures, but haven't found conclusive evidence yet. Cosmic strings remain theoretical, predicted by some physics theories extending beyond the standard model, but not required by any observations. They might not exist at all, but if they do, they'd be among the strangest objects in the universe, primordial cracks left over from the universe's birth. Thin as an atom, but stretching across cosmic distances, testament to how phase transitions in the early universe might have left permanent scars on the fabric of reality. Some interpretations of physics suggest our universe might not be alone. The multiverse hypothesis proposes that countless other universes exist beyond our own, each potentially with different physical laws, different constants of nature, different configurations of matter and energy. Several ideas lead to multiverses. Eternal inflation suggests that while inflation ended in our region, creating our observable universe, it continues elsewhere, constantly spawning new bubble universes with potentially different properties. Quantum mechanics' many worlds interpretation suggests the universe splits every time a quantum measurement occurs, creating parallel realities for every possible outcome. String theory allows for perhaps 10,500 different possible universes, each corresponding to different ways extra dimensions could be configured. If the multiverse exists, we might be just one universe among an infinity of others. Some universes might have stronger gravity or weaker electromagnetic forces. Some might contain no stars because their physics doesn't allow fusion. Others might be far more hospitable to life than ours. We happen to observe a universe compatible with our existence, because if it weren't, we wouldn't be here to observe it. A selection effect called the anthropic principle. But here's the challenge. If other universes exist beyond our cosmic horizon, separated from us by infinite space or different dimensions, how could we ever detect them? They might be fundamentally unobservable, making the multiverse hypothesis unfalsifiable, neither provable nor disprovable. Some scientists argue this takes the idea outside the realm of science into philosophy or metaphysics. Still, the multiverse emerges naturally from several serious physics theories. It might be real, even if we can never prove it. We might be one island of reality in an ocean of universes, our physical laws just one possibility among infinite variations. Our existence the result of being in one of the rare universes where complexity and consciousness can emerge. Time seems to flow in only one direction. We remember the past, but not the future. Eggs break, but don't spontaneously reassemble. Coffee cools, but never spontaneously heats up. Entropy, disorder, increases. This one-way flow of time is called the arrow of time, and it's one of physics' deepest mysteries. Here's the puzzle. Most fundamental physics equations work equally well running forward or backward in time. Newton's laws, Maxwell's equations of electromagnetism, even Einstein's relativity, they don't distinguish past from future. If you filmed particles obeying these laws and played the film backward, the reversed motion would still obey the same laws. Time symmetry appears fundamental, yet we clearly experience time flowing in one direction. The resolution might involve thermodynamics and entropy. The second law of thermodynamics states that entropy, disorder, tends to increase in closed systems. A broken egg has higher entropy than an intact one. Heat dispersed throughout a room has higher entropy than heat concentrated in a hot cup. Systems naturally evolve toward higher entropy states. But why? The answer might trace to the Big Bang. The early universe was in an extraordinarily low entropy state, highly ordered, uniform, dense. Since then, entropy has been increasing as the universe expands, cools, and structures form, and eventually decay. The arrow of time might point in the direction of increasing entropy, from the ordered beginning toward the disordered distant future. So we perceive time flowing forward because entropy increases, and entropy increases because the universe started in a low entropy state. But why did it start that way? That question remains unanswered. The arrow of time emerges from cosmic initial conditions we don't fully understand, connecting our daily experience of time's passage to the universe's birth and ultimate fate. In quantum field theory, the vacuum of space should have energy, contributions from virtual particles, and quantum fluctuations. Physicists can calculate what this vacuum energy should be, and the answer is enormous, about 10^120 times larger than what we actually observe. This discrepancy, 120 orders of magnitude, is called the cosmological constant problem, and it's the worst prediction in physics. Here's why it matters. Vacuum energy acts like dark energy, affecting the universe's expansion. If the vacuum energy were as large as theory predicts, the universe would have expanded so rapidly that structures, galaxies, stars, planets could never have formed. Life wouldn't exist. Yet the actual measured value of dark energy is tiny, just barely enough to cause the observed acceleration, but not so much that it rips everything apart. Why is the vacuum energy so much smaller than predicted? We don't know. Maybe there's some cancellation mechanism we haven't discovered, where positive and negative contributions nearly balance. Maybe there's new physics we don't understand that sets the vacuum energy. Or maybe the anthropic principle applies. In a multiverse with different vacuum energies, we necessarily find ourselves in a universe where the value allows life. The problem remains unsolved after decades. Either our understanding of quantum field theory is wrong, or our understanding of gravity is wrong, or there's something fundamental we're missing. This discrepancy between theory and observation sits at the intersection of quantum mechanics and general relativity, the two pillars of modern physics that we've never successfully unified. Solving the cosmological constant problem might require new physics that reconciles these theories. Enrico Fermi, during a casual lunch conversation in 1950, asked a simple question: where is everybody? If the universe is so vast and old, filled with hundreds of billions of galaxies, each containing billions of stars, many with planets, why haven't we detected any signs of other intelligent civilizations? This puzzle is the Fermi paradox. The numbers suggest we shouldn't be alone. The Milky Way contains several 100 billion stars, many billions of years older than the Sun. If even a tiny fraction have planets that develop life, and a tiny fraction of those develop intelligent life, and a tiny fraction of those develop technology and expand into space, there should be many civilizations out there. Some might be millions of years ahead of us. Where are they? Proposed solutions range widely. Maybe life is extraordinarily rare. The chain of unlikely events leading to complex life might be longer than we think. Maybe intelligence rarely evolves, or technological civilizations destroy themselves quickly. Maybe space travel is harder than science fiction suggests, and civilizations stay confined to their home systems. Maybe they're here but hiding, or we're in a cosmic nature preserve, deliberately uncontacted, or perhaps we're truly alone, the first or only intelligence in our galaxy, maybe in the observable universe. The responsibility that would entail is staggering. Consciousness might be incredibly rare, and if we destroy ourselves, it might vanish from this region of space entirely. The Fermi paradox remains unresolved. We search the skies for signals, finding only silence. Maybe we haven't looked long enough or carefully enough. Maybe the answer is simpler than we think. Or maybe the silence itself is the answer, profound and unsettling. The holographic principle suggests something strange. All the information contained in a volume of space can be encoded on its boundary surface, like a three-dimensional image encoded on a two-dimensional hologram. This means our three-dimensional reality might be a projection from information stored in two dimensions. This idea emerged from studying black holes. The entropy, the amount of information a black hole can contain, is proportional to its surface area, not its volume. This seems wrong. We'd expect the amount of information to scale with volume. But for black holes, it's the surface that matters, as if information is somehow encoded on the event horizon. Physicists realized this might apply generally. Any region of space has a maximum information capacity proportional to its boundary area. The universe itself might be holographic, with all physical processes we observe being projections from information encoded on a distant cosmic boundary. This doesn't mean reality is an illusion. The hologram is just as real as the three-dimensional image it encodes. But it suggests space and dimension might not be fundamental. At the deepest level, the universe might be described by a theory operating in fewer dimensions, with the three-dimensional space we experience emerging from underlying two-dimensional physics. The holographic principle has influenced attempts to unify quantum mechanics and gravity, particularly in string theory, where it's been precisely formulated in certain cases. But whether our actual universe is holographic and what that would mean for our understanding of reality remains uncertain. It's a profound idea suggesting that space itself, which seems so fundamental to existence, might be secondary, a convenient description arising from something more basic. What happened before the Big Bang? It's a natural question, but it might not have an answer. Or the answer might be that the question doesn't make sense. If time itself began with the Big Bang, then there is no before. Asking what came before the Big Bang is like asking what's north of the North Pole. The question assumes a direction that doesn't exist. In general relativity, space-time has a beginning at the Big Bang singularity, a point where density and temperature become infinite, and the equations break down. Our physics can't describe what happens at a singularity or whether anything existed before it. We can trace the universe's history back to fractions of a second after the Big Bang, but we can't penetrate to the initial moment itself, let alone before. Some theories suggest the Big Bang wasn't actually a beginning, but a transition, perhaps from a previous collapsing universe that bounced into expansion, or from a different phase of existence. Some propose that time is emergent, not fundamental, arising from timeless quantum laws. Others suggest the universe is eternal, with no absolute beginning. We simply don't know. The extreme conditions at the Big Bang exceed anything we can test experimentally or calculate reliably. Our theories break down. We're left with speculation informed by incomplete physics. The beginning of the universe, if there was one, remains wrapped in mystery, perhaps ultimately beyond our ability to understand. The question of origins might be one that science can't fully answer, not because of any limitation in principle, but because the conditions involved exceed the reach of our theories. The fundamental constants of nature, the strength of gravity, the electromagnetic force, the mass of electrons and quarks, appear precisely calibrated to allow complex structures and life. Change any of these values slightly, and the universe would be sterile, unable to form stars, atoms, or anything resembling life. If gravity were slightly stronger, stars would burn too hot and fast, exhausting their fuel before life could evolve. Slightly weaker, and stars might never ignite fusion at all. If the electromagnetic force were different, atoms might not form, or chemistry would work differently, perhaps unable to create the complex molecules needed for life. The list of such coincidences is long and troubling. This fine-tuning seems improbable. Why should the constants have values so precisely suited to our existence? Several explanations have been proposed. Maybe there's an underlying theory that requires these specific values. The constants aren't arbitrary but mathematically necessary. Maybe we're observing selection bias. In a multiverse with varying constants, we necessarily find ourselves in a universe compatible with observers. Or maybe we're just lucky, and no deeper explanation exists. The fine-tuning problem troubles some physicists because it seems to require explanation. The universe appears designed for life, yet physics aims to explain things through impersonal laws, not purpose or design. The anthropic principle, we observe what we observe because we exist, is either profound or a cop-out, depending on your perspective. No consensus exists on how to interpret fine-tuning. It might point toward new physics, toward a multiverse, or toward limits in what science can explain. Or perhaps future theories will show the constants aren't independent. They're all determined by one deeper principle we haven't discovered yet. Einstein's equations of general relativity permit solutions called wormholes, hypothetical tunnels connecting distant points in space and time. A wormhole could theoretically link two locations millions of light years apart, allowing travel between them in moments rather than millennia. Or it might connect different times, potentially enabling time travel. Wormholes are mathematically possible, but creating or maintaining one faces enormous obstacles. The equations suggest wormholes would collapse almost instantly unless held open by exotic matter with negative energy density, something never observed and possibly forbidden by quantum mechanics. The energy requirements might be impossibly large, requiring the mass energy of stars or galaxies to create a traversable wormhole. Even if you could create and stabilize a wormhole, causality problems arise, especially if it allows time travel. You could potentially travel through the wormhole into your own past and prevent yourself from entering the wormhole, creating a paradox. Some physicists argue such paradoxes mean time travel is impossible, while others propose resolutions involving parallel timelines or self-consistent loops. Wormholes remain firmly in the realm of speculation. They're permitted by the equations, but require conditions we've never observed and probably can't create. They're useful for exploring the mathematical structure of general relativity and pondering the nature of space and time. But as practical shortcuts across space or doorways to the past, they remain science fiction. The universe seems designed to prevent the kinds of causality violations wormholes might allow, protecting the logical consistency of reality. If the universe continues expanding forever, accelerating due to dark energy, its ultimate fate might be heat death, a state of maximum entropy where no energy gradients remain to do work, where nothing can happen anymore because everything has reached equilibrium. Over trillions of years, stars will exhaust their fuel and die. New star formation will cease as gas becomes too dispersed. Galaxies will dim, filled with white dwarfs, neutron stars, and black holes. Eventually, even black holes will evaporate through Hawking radiation. Protons might decay, dissolving all remaining matter. The universe will consist of photons and other particles spreading ever more thinly through exponentially expanding space. Temperature differences will disappear. Energy will be distributed uniformly, unable to flow from hot to cold because there is no hot or cold anymore. Just a uniform, low-energy bath approaching absolute zero. No work can be extracted. No processes can occur. No change is possible. Time becomes meaningless in a universe where nothing happens. This fate is called heat death, though it's really a cold death, the universe reaching a state of maximum entropy, thermal equilibrium at nearly absolute zero. It's a peaceful end, if depressing, not a violent destruction, but a gradual fading into stillness and silence. Of course, our understanding could be wrong. Dark energy might change, expansion might reverse, new physics might intervene. But based on current observations, heat death appears to be the universe's likely destiny. Trillions upon trillions of years from now, a long, slow decline into equilibrium and eternal stillness. Some physicists have proposed controversial ideas connecting consciousness to quantum mechanics. The measurement problem in quantum mechanics asks, when does a quantum system in superposition, existing in multiple states simultaneously, collapse into a definite state? Standard interpretations say measurement causes collapse, but what counts as measurement? Some have suggested consciousness plays a role, that observation by a conscious mind causes quantum collapse, turning possibilities into actualities. This idea has appeal because it gives consciousness a fundamental place in physics, but it's deeply problematic. It seems implausible that the universe needed conscious observers to function before life evolved. And experiments suggest quantum collapse doesn't require consciousness. Any interaction with the environment causes decoherence and apparent collapse. Most physicists reject consciousness-based interpretations, viewing them as unnecessary and untestable. Quantum mechanics works perfectly well without invoking consciousness. The measurement problem likely has solutions involving decoherence, many worlds interpretation, or other approaches that don't require consciousness to play any special role. Still, the relationship between mind and matter remains mysterious. How does consciousness arise from physical processes? Why is there subjective experience at all? These questions lie at the boundary of physics, neuroscience, and philosophy. Whether consciousness has any role in fundamental physics is doubtful, but the fact that matter organized into brains can become aware, can ponder quantum mechanics and its own existence, remains deeply puzzling, perhaps the deepest puzzle we face. The anthropic principle is a curious form of reasoning. We observe the universe has properties compatible with our existence, because if it didn't, we wouldn't be here to observe it. This sounds circular, almost trivial, but it has implications for how we interpret the universe's apparent fine-tuning. Consider that many physical constants seem precisely calibrated for life. The weak anthropic principle simply notes that in any universe we could possibly observe, these constants must allow observers to exist. We're experiencing selection bias. The strong anthropic principle goes further, suggesting the universe must have properties allowing consciousness to develop eventually. Though why this should be remains unclear. Some view the anthropic principle as a profound insight. In a multiverse with varying properties, we necessarily find ourselves in one of the rare universes capable of supporting life. We're not observing a miracle, but experiencing selection effects at cosmic scale. Others dismiss it as a non-explanation, a way of avoiding the question of why our universe has the properties it does. The anthropic principle is useful for making predictions. If we're typical observers in a multiverse, we should expect to find ourselves in a universe that's reasonably common among those supporting observers, not in an extremely rare or special one. This reasoning has been used to predict values of certain cosmological parameters before they were measured. Whether the anthropic principle explains anything or merely restates the obvious depends on your perspective. It doesn't tell us why the universe permits life, but it might tell us we're asking the wrong question. In a vast multiverse, perhaps no explanation is needed beyond. We're here because here is one of the places where here can be. It's either the deepest insight into cosmic structure or a tautology dressed in philosophical clothing, or perhaps both simultaneously. The original inflation theory proposed that the universe underwent a brief period of exponential expansion in its first moments. Then inflation ended, and normal expansion continued. But eternal inflation suggests a different picture. Inflation never completely ends. It stops in some regions, creating bubble universes like ours, but continues in others, constantly spawning new bubbles throughout a larger, eternally inflating space. In this picture, our Big Bang wasn't the beginning of everything, just the beginning of our local bubble. Inflation is still happening elsewhere, and always will be, creating infinite bubble universes in an eternally inflating multiverse. Each bubble could have different properties, different constants, different laws of physics, different numbers of dimensions, depending on how fields settle when inflation ends in that region. The bubbles are causally disconnected. They can't interact or communicate because space between them expands faster than light. We're confined to our bubble, unable to observe or visit others. If eternal inflation is correct, our observable universe is a tiny patch in one bubble among infinite bubbles, each containing its own vast space filled with galaxies. This theory emerges naturally from inflation's physics. Once inflation starts, quantum fluctuations ensure it ends at different times in different places. Where it ends slowly, those regions continue inflating while the rest stops, creating a fractal pattern of inflating regions, spawning new bubbles forever. Eternal inflation is elegant, but raises questions. If universe creation is ongoing and infinite, concepts like the universe's age become local, not universal. The multiverse has no beginning in time, just local beginnings for individual bubbles. Testing this theory is extremely difficult since other bubbles are unobservable, leaving eternal inflation in uncertain territory between physics and metaphysics. The universe might be infinite in spatial extent. Observations suggest space is flat or nearly flat, not curved back on itself. A flat universe extends infinitely in all directions, never looping back, containing infinite volume and possibly infinite matter. In an infinite universe, everything that's possible must happen somewhere. In fact, must happen infinitely many times. The random arrangement of matter and energy means that, given infinite space, every possible configuration occurs. This includes duplicates of you, of Earth, of everything. Somewhere, infinitely far away, there might be another planet identical to Earth, with someone exactly like you reading these exact words. This sounds absurd, but it's a logical consequence of infinity, combined with quantum mechanics' probabilistic nature. If possibilities are finite but space is infinite, repetition is inevitable. Of course, the distances involved are incomprehensibly vast. Your nearest duplicate might be farther away than 10^10^29 meters, a number so large it's meaningless. You'll never meet them. Light from there will never reach here. Whether the universe is actually infinite or just very large but finite remains uncertain. We can only observe a finite portion, the observable universe, and we can't measure the curvature precisely enough to be sure whether space is exactly flat, infinite, or slightly curved, finite. The universe might wrap around itself in ways we can't detect, making it finite but unbounded, like a higher dimensional sphere. Infinity is strange. An infinite universe contains everything possible, repeated endlessly in regions forever beyond our reach. Or perhaps the universe is finite, and we're all there is, a bounded cosmos containing a limited, unique arrangement of matter, singular and alone. Quantum mechanics' central mystery is the measurement problem. Quantum systems exist in superpositions, multiple states simultaneously, until measured, whereupon they collapse into one definite state. But when and how does collapse occur? What counts as measurement? Before measurement, an electron might be in a superposition of spinning clockwise and counterclockwise simultaneously. Measure it, and you find one spin or the other, never both. The act of measurement seems to force the electron to choose. But electrons don't have agency. What actually happens during measurement? The Copenhagen interpretation says measurement causes collapse, but doesn't specify the physical mechanism. The many worlds interpretation says the universe splits. Both outcomes occur in different branches of reality, and you only observe one. Decoherence theory suggests interaction with the environment causes apparent collapse without requiring actual collapse. Other interpretations propose different solutions. After a century, physicists still debate what measurement means. The mathematics of quantum mechanics works perfectly. It predicts experimental results with extraordinary precision. But its interpretation, what it tells us about reality, remains controversial. Does the wave function represent physical reality or just our knowledge? Do particles have definite properties before measurement? Does observation create reality? These aren't idle philosophical questions. They touch on the nature of existence itself. Quantum mechanics suggests reality is fundamentally different from our everyday experience, but we don't agree on how different. The measurement problem persists as a deep puzzle at the heart of physics, a reminder that despite our technological mastery of quantum effects, we might not truly understand what quantum mechanics is telling us about the nature of reality. Some approaches to quantum gravity suggest time isn't fundamental but emergent. It arises from more basic, timeless laws operating at the deepest level of reality. This challenges our intuition that time is fundamental, one of reality's basic dimensions. The idea emerges from attempts to unify quantum mechanics and general relativity. The Wheeler-DeWitt equation describing quantum cosmology contains no time variable. It's a timeless equation describing a static quantum state. Time appears only when you consider subsystems within the universe, emerging from correlations and changes in quantum states. If time is emergent, what exists fundamentally? Perhaps a timeless quantum state containing all possible configurations of the universe simultaneously. Time emerges when we look at parts of this state, seeing change and evolution because we're part of the system, experiencing it from within rather than viewing it from outside. This perspective suggests the flow of time we experience, the arrow from past to future, isn't fundamental but arises from our embedded position within the universe. At the deepest level, past, present, and future might coexist in a timeless quantum reality, with time being something that only appears when systems become complex enough to have histories and memories. These ideas remain speculative, part of the ongoing struggle to reconcile quantum mechanics with gravity. But they suggest that time, which seems so fundamental to existence, might be secondary, a useful description emerging from timeless quantum laws, like temperature emerging from molecular motion. If true, the universe's deepest nature might be radically different from anything we experience, with time itself being a property of our limited perspective rather than reality's foundation. The Bekenstein bound establishes a maximum amount of information that can be contained in a given region of space. This limit is proportional to the region's surface area, not its volume, and relates to the holographic principle. Specifically, the maximum entropy, information content, in a sphere is proportional to its surface area measured in Planck units. For a sphere 1 meter in radius, the maximum information is about 10^69 bits. This seems enormous, but it's finite, implying the universe has limits on information storage. This has strange implications. If you tried to pack too much information into a region, say by compressing matter beyond a certain density, it would collapse into a black hole. The black hole's event horizon has area proportional to the information it contains, and you can't add more information without expanding the horizon. The universe seems to have a maximum storage density, like a cosmic hard drive with finite capacity. This limit connects to thermodynamics, quantum mechanics, and gravity in deep ways we don't fully understand. It suggests information is fundamental, perhaps more fundamental than matter or energy, and that space has an intrinsic graininess at the Planck scale where information storage reaches its limits. For the observable universe, the Bekenstein bound implies a maximum information content of about 10^120 bits, an enormous number, but finite. This means there are only finitely many possible states the observable universe could be in, and only finitely many possible histories. In an infinite multiverse, every possible state would occur somewhere, repeated infinitely. But within our observable bubble, possibilities are limited. Reality has boundaries, even if those boundaries are almost incomprehensibly large. According to our understanding of particle physics, the Big Bang should have created equal amounts of matter and antimatter. When matter meets antimatter, they annihilate into pure energy. So the universe should have annihilated itself almost immediately, leaving nothing but photons. But we exist. The universe is made of matter, not antimatter. Somewhere in the early universe's history, matter gained a slight advantage, about one extra matter particle for every billion matter-antimatter pairs. After all the antimatter annihilated with an equal amount of matter, that tiny excess remained, becoming everything we see: galaxies, stars, planets, people. Why this asymmetry? We don't fully know. The process is called baryogenesis, and it requires three conditions called Sakharov conditions. Baryon number violation, processes that create more matter than antimatter. Charge parity violation, matter and antimatter behaving slightly differently. And thermal non-equilibrium, conditions where creation and annihilation rates differ. All three conditions likely occurred in the early universe, but we don't know the exact mechanism. The asymmetry is incredibly small, about 1 part in a billion, but absolutely crucial. Without it, the universe would be empty, filled only with photons cooling into darkness. We exist because of a tiny imbalance in the first moments after the Big Bang, an asymmetry so slight it would seem negligible. Yet it made the difference between a universe of light and matter versus a universe of only light. Understanding why this asymmetry exists remains one of cosmology's great unsolved problems, a puzzle about the universe's initial conditions that determined everything that followed. After the Big Bang, the universe was hot and opaque, filled with plasma glowing with thermal radiation. About 380,000 years later, it cooled enough for atoms to form, and the universe became transparent. This is when the cosmic microwave background was released. But then came the cosmic dark ages, a period lasting hundreds of millions of years when the universe was dark, except for the fading glow of the Big Bang. No stars existed yet. The primordial hydrogen gas slowly cooled, filling space uniformly, absorbing any photons that happened to pass through. It was a vast, dark, cooling ocean of neutral hydrogen, slowly settling under gravity's patient pull. This era ended when the first stars ignited, perhaps 100 to 200 million years after the Big Bang. These first stars, made only of hydrogen and helium with no heavy elements, were likely massive and short-lived, burning fiercely for just a few million years before exploding. Their ultraviolet light began reionizing the surrounding hydrogen, creating bubbles of ionized gas that expanded and merged. Eventually, enough stars formed that their combined radiation reionized the entire universe, ending the Dark Ages and beginning the era of light we inhabit now. But for those hundreds of millions of years, the universe was a dark, quiet place, waiting for gravity to pull matter together densely enough to ignite fusion and bring light back to the cosmos. Those dark ages are hidden from direct observation. No light escaped, no signals reach us from that era. But we can infer what happened from theory and from observations of the period just after, when the first stars appeared. It was a formative time when the universe's structure began to emerge from the smooth, uniform beginning. Perhaps the deepest question, why does anything exist? Why is there something rather than nothing? Science can trace the universe's history back to moments after the Big Bang, can describe how matter organized into structures, how stars formed and planets coalesced and life emerged. But it cannot answer why there is a universe at all. Some philosophers argue nothing is unstable, that quantum mechanics allows something to arise from nothing through vacuum fluctuations. But this requires quantum fields, which are something, not nothing. Others suggest the universe is eternal, without beginning, sidestepping the question of creation. Still others propose that existence is necessary, that nothingness is logically impossible, though why remains unclear. Perhaps the question is unanswerable. Science explains how things work using natural laws, but those laws themselves exist. They're something rather than nothing. You can ask why these laws exist, but any answer would invoke other principles which also exist. You never escape the question of why there's something. Maybe existence needs no explanation. Maybe the universe simply is, without reason, without cause, a brute fact that admits no deeper understanding. This might seem unsatisfying. We want reasons, causes, explanations. But perhaps at the most fundamental level, explanation reaches its limit. Reality grounds itself in nothing deeper than itself. Or perhaps there is an answer we haven't conceived, a way of thinking about existence that transcends our current understanding. The question stands at the boundary of science and philosophy, probably the most profound question we can ask, and possibly one we'll never answer. We've journeyed through space together, from the familiar moon slowly drifting away to the deepest mysteries at reality's foundation. We've explored stars and galaxies, black holes and dark matter, the universe's beginning and possible endings. We've touched on questions that have puzzled humanity for millennia, and problems that emerged only recently from our growing understanding. And yet, despite everything we've learned, the most profound questions remain beautifully, mysteriously unanswered. Why does anything exist? Why these laws of physics and not others? Why this universe? Science has revealed the cosmos in breathtaking detail, mapping its structure across billions of light years and down to subatomic scales. But the question of why there is something rather than nothing, remains beyond our reach. Perhaps that's fitting. The universe is vast and ancient, filled with wonders we're only beginning to understand. Dark matter and dark energy make up 95% of the universe, yet we don't know what they are. Consciousness arises from matter, yet we can't explain how. The measurement problem in quantum mechanics persists after a century of debate. The reconciliation of quantum mechanics and gravity eludes us. These unsolved questions don't represent failures, but frontiers, reminders that mystery remains, that wonder persists, that the universe still holds secrets. We've learned so much, and yet there's infinitely more to discover. Each answer reveals new questions, deeper puzzles, wider vistas of unknowing. And perhaps that's the most comforting thought as you drift toward sleep. The universe is larger and stranger than we imagine, filled with beauty and mystery that will outlast us all. The questions endure, patient and eternal, waiting for future generations to probe them. to add their own small contributions to humanity's ongoing conversation with the cosmos. And so we've reached the end of our journey through space tonight. 100 facts, 100 glimpses into the cosmos that surrounds us, holds us, and in a very real sense, created us from its own substance billions of years ago. We began close to home, with the moon drifting slowly away and the edge of space just 62 miles above your head. We ventured outward through the solar system, past Mars with its ancient storms, and Europa with its hidden ocean, past Saturn's delicate rings and Neptune's century-long years. We explored stars being born and dying, black holes warping space-time, galaxies colliding in slow motion across billions of years. And we ended with mysteries, questions that touch the foundations of existence itself, puzzles about time and consciousness, and why there is anything at all. The universe is patient with our questions. It's been here for nearly 14 billion years, and it will be here long after we're gone, continuing its slow evolution from the hot, dense beginning toward whatever ending awaits. Stars will continue to burn, galaxies will continue their stately dance, and the cosmos will unfold according to laws we're only beginning to understand. Sleep well, knowing you're part of something vast and ancient and ongoing. You're made of atoms forged in stellar cores, organized by billions of years of evolution into a form capable of understanding, however imperfectly, the universe that made you. That's no small thing. That's everything. Good night.